Yes, 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 yes.
Because the light is
Yes.
too strange.
So we should put it more in this direction. This just, well, I will not use much blackboard, just two pictures like that. Yeah, we can start, yes.
So let's start. So it's my pleasure to introduce our first speaker, Stirad Klimchik from the Institut de Mathématiques de Marseille, who will be telling us about superintegrability, symmetry, and point particle T-duality.
Okay, thank you. So first I thank the organizers for having invited me and also for organizing this nice meeting. I will speak about classical mechanics, so it will be a trip to 19th century, if you wish. But honestly, when I was doing things around that, I discovered that until now there is a big amount of people working in the classical mechanics, and especially they use the notion of canonical transformation in substantial way. And those people work on integrability and superintegrability. So still, since 60s, this one can call it the mainstream. There are a lot of papers and new results. And basically, those people study question that if you are given a phase space and a Hamiltonian, whether they can find a canonical transformation which put it in some canonical form which is called action angle variables. So they want to know whether the system which they study is integrable or is not integrable. And even within integrable system you have subcategories like superintegrable system, etc. So those people have produced a lot of interesting results. They have studied a lot of Hamiltonians. They constructed a lot of interesting canonical transformation. And so I use all those results with a different motivation. So for me, it will not be a question to study whether given dynamical system is integrable or superintegrable. My concern is to take two dynamical systems which look differently and to ask whether they can be related by canonical transformation. So this question could have been asked 200 years ago. It was not, apparently. But it's asked because it emerged in string theory. And so I start with my transparencies here. So there is some motivation for a study of the point particle T-duality, and it comes essentially from string theory and from the study of Poisson-Lie T-duality. So I will explain those motivations, and then I will turn directly to this classical mechanics story, and I construct some examples in one dimensions, which are already non-trivial. And then I will show how I will go to higher dimension when things become, of course, more interesting. And the basic tools which I will use is superintegrability and symmetry. So I will, from technical point of view, heavily use the results which are already in the market, but in some sense I complete them and I put them together. And I explain all the construction on two concrete examples. I will show that the conformal mechanic of, if you wish, Calogero model with inverse square potential is T-dual to standard Coulomb scattering, which has 1 over r fall-off of potential, so you would not say it at the first sight. And then also the true T-duality, which takes in account also the geometry of the background, is that the space of negative constant curvature, if you wish, Euclidean ADS, is T-dual to the flat one from the point of point particle physics. So actually I will not quite follow chronologically those 5 points. First I will try to construct the T-duality example to show them here they are. And then I will explain how I obtain them, just to avoid the risk of running out of time. I will accumulate all the results, you know, in the first pages. So what about string T-duality? The story starts there. This slide, it's almost identical to the slide of Sibyl. You know, you have, oh, what I'm doing. Oh, yes. So you have two sigma models. I avoid the problem of topological non-trivial H. For me, it's just G and B fields, and G tilde and B tilde fields. So we have two sigma models living on different targets and having different geometries, you know, gravitational and B field. And if you construct the first order Hamiltonian formalism for those actions, second order actions, it turns out that the symplectic forms are standard Darboux for this model and standard Darboux for the other model. So this delta is a D, but in infinite dimensional context, people always noticed as a delta, not as a D, so I follow the tradition. But the Hamiltonians are written here, and of course they have the variables x and p, but also they contain information about the original background. So you see G here, and you see B here, and G also here. So you can recover the second order action starting from this Hamiltonian. This is equivalent description of the same dynamics, but this is the first order description. And you can also go from second order description on the tilde side to the first order description. You get a similar formula, but you put everywhere tildes. And now I think that the idea of relating the T-dual models by canonical transformation maybe goes back to Arkady in abelian case, but the first definition, which would cover all cases, abelian, non-abelian, was probably formulated by Alvarez, Gomez, Lozano. And they simply said that the model S tilde is T-dual to the model S if there exists the canonical transformation X tilde, P tilde in terms of X and P such that one Hamiltonian goes to the other. It's as simple as that. And what is interesting about the story that the geometry of this model may be very different than this one. Even topology of the target may be different. But somehow canonical transformation takes care of that. And you really can find explicitly X tilde, for example, for the case of non-abelian T-duality or Poisson-Lie T-duality. You can find explicit expression relating X tilde and P tilde with X and P, such that one Hamiltonian goes to another one. The question whether there exists some other generalization of Poisson-Lie T-duality, of course, we have to construct such a canonical transformation, and this is not an easy thing. Now, there is a big drawback with Poisson-Lie T-duality and all T-dualities except of abelian one. And this drawback is the problem of zero modes. So, but I'm not yet there. Yes. So let me comment this transparency. So point particle T-duality. Now I'm going to define it. What it means. I have two second order action. So now I don't have gravitational field and B field, but I have gravitational field and electromagnetic field. So we have electromagnetic gravitational background. V is electric potential, A is a magnetic, and G is a background metric. And to construct the action of a sigma model in one dimension, if you wish, in the standard way, here is the action. Here is the dual action. You go to the Hamiltonians, which are standard one, which you find in every textbook. And now the definition is exactly the same as in the string theory. You say that S tilde is T dual to S if there exists canonical transformation which relates those Hamiltonians in this way. So this is analogy, and still people for a long time believed somehow that the T-duality is a stringy effect. So such a canonical transformation which relates X and P and X tilde and P tilde exist only in the string case, and somehow in point particle dynamics we don't have such examples. But it turns out it's not the case, that I will try to argue that there are many, many such examples, much more than in string theory, and it's not that complicated to construct them. Now, why this should be interesting for string theory? The reason is, and I'm coming to that, which probably is not quite known or not much discussed, is that, you know, here, well, I formulate it in this way. So maybe you agree that the point particle T-duality may be a problem interesting on its own. But it may be also relevant for string T-duality because, as I said, except of abelian T-duality, all other known T-dualities on the market, like non-abelian one or Poisson-Lie T-duality, they suffer from a drawback that the duality is not a perfect one. It's in fact, I use the word dismembered. So what happens actually that if you take a sigma model of one manifold, you have to throw away some zero modes of the string on both sides, on non-tilde side and on tilde side. And only if you throw out appropriate zero modes, you recover T-duality. So it's not a honest T-duality, full-fledged. And there is some reason why this happens is that, for example, Poisson-Lie T-duality relates the sigma models on two coset space, D over H and D over H tilde. And so if you have a closed string here, you claim that there exists another closed string configuration which is dual to that. So there is a closed string here, and there should be a closed string here which is dual to that. And the way how do you construct this closed string here out of this closed string, that you lift first this closed string to the Drinfeld double, you have this map D to DH, and then you project it to D over H tilde. But there is a problem with this construction, that if you lift this configuration from DH to the Drinfeld double, it can get torn. It will not be a closed string here. And so what you have to do, you have to consider only such closed string configuration here which are lifted to closed strings here. And it turns out that it can be done simply by throwing away some appropriate zero modes, which have so-called non-abelian momentum equal to 1. Once you do that, then you are safe. On the safe side, you project and you recover closed string here. But of course, the image of this map, you will not cover all closed string here, only some of them. Actually, you have to throw away some other set of zero modes. And if you do that, you obtain Poisson-Lie T-duality. In spite of this drawback, it's a useful concept, as we have seen on many talks here, as a solution generation technique. But if you really want to promote it to the symmetry of string theory, you have to solve the problem of the zero modes. So, by the way, this problem shows why you cannot produce the examples of point particle T-duality starting from string T-duality. You could think, okay, if I have a string T-duality examples, I really do some kind of dimensional reduction. I get back to the ordinary mechanics, and I have some p-duality example. You don't have, because if you do this projection down, you obtain strictly zero. You lose all zero modes. So the motivation is to study t-duality in the point particle case on its own, and eventually to try to glue it, this t-duality picture, to the string picture to obtain the full-fledged stringed t-duality. So this is a motivation. But once you study this point particle t-duality, you discover that this problem on its own interesting, because you need some tools how to produce such examples. And these tools comes from integrability and symmetry. Is remarkable that the same tools are useful in string theory, where the question or the problems related to t-duality are much related also to the symmetry of the background, or Poisson-Lie symmetry of the background, or to the integrability of the sigma model. So these notions of integrability and symmetry are important on string side and also on point particle side. Okay. So let me give some simple examples. Here, this is a sorry, what I'm doing. This is a Calogero Hamiltonians. In fact, this is a pair of Calogero Hamiltonians. No, this is not Calogero. This is Calogero. So look, those two Hamiltonians differ just by a choice of coupling constant G. Yeah. And we ask whether it exists a canonical transformation which relates these two Hamiltonians. It means whether the point particle feels the strength of the interaction. And it turns out that it doesn't. That if you take this canonical transformation, which is written here, then one Hamiltonian goes to another one. You have a sort of running coupling constant. So the dynamics of the model is immune to the change of the strength of the coupling, except you cannot go to zero, because this changed the game. The G has to be non-zero. And this thing is a Honet's canonical transformation, is bijection, and realize the simple example of point particle t-duality. There is no gravity here. We are in one-dimensional space. You know that in one-dimensional space, every geometry is flat. But there is still some electric potential, so we have two different electric potential, and they are related by t-duality. Now, let's go to the next example. Is harmonic oscillator with two different frequencies. Is one frequency and there is another frequency. And the question, does it exist a canonical transformation such that it would render the point particle immune to the concept of frequency? So does it exist? And it does not. You know, there is no t-duality. You know, the particle feels the frequency. Of course, you can construct locally the map. This is a canonical transformation, such that one Hamiltonian goes to another one, and that the transformation is canonical. But this is not a bijection, you know. Depending on the configuration of frequencies, this map is either not injective or not surjective. So as you see that even in the simple cases, the problem is open, so some Hamiltonians give example of t-duality, and some simple Hamiltonians, they do not. Now, let us study the potentials. Still we are in one dimension. So this potential is called the Calogero-Sutherland, and it has exponential fall-off. And this is a standard Calogero potential, and it has a polynomial fall-off. So does it exist a canonical transformation? And it does. It is here, and so those systems are equivalent, dynamically equivalent. So now we want to go to high dimension and to include gravity in the game. And so such example was constructed by me some 2 years ago. In 4 dimension, it was a bit, you know, artificial, let's put it clearly. So there was some gravitational field which I interpreted as a deformed Euclidean black hole, but whatever it means, and some electric fields, but this model was not very realistic physically, but actually it exhibited the point particle T-duality. If I change some parameter in the model, it changed the geometry, but it did not change the dynamics. But now I propose, I still did not publish this thing. I'm in the middle of calculation. I think it's 95% is well done and correct, so maybe I have to check some small things, but basically the picture which I'm showing you, it's complete and correct. And so I used the 2 notions, superintegrability and symmetry, to construct higher dimensional examples. How I did it, I will explain you in 10 minutes, but first I show you what it gave, you know, just to have those examples. And so we take a Hamiltonian, which is standard Coulomb one, and this is a Calogero one. We are in whatever dimension you wish, but let's say we are in 3 dimensions. And you know, this Calogero Hamiltonian is much studied because it gives example of conformal field theory in 0+1 dimension. And so this is a reason that this model is much studied. This model is also very much studied. Look, it's repulsive Coulomb potential, so it describes the scattering of a charged particle on the Coulomb potential. So those models are both very much studied, and the question is whether they are T-dual, one to another, whether they are dynamical equivalent. So is there a canonical transformation which takes one Hamiltonian to another one? Yes, it is. It's a bit complicated object because you see here x tilde and here is p tilde. On the right hand side you would like to see x and p, and instead of that you see k, c, psi, s, and whatever, h, big T, etc. All those symbols which are here written depend on p and x. So for example, this vector k depends on p and x in this way, vector s in this way. Function c depends on this way, where t depends on this way on p on x. And psi depends on this way, where m depends on this way on p and x. That's just a complicated beast. And it's clear that one would not guess it, that this has to be derived from some principles. But the result is this. And so the problem, Coulomb problem and Calogero problem are equivalent. What is interesting that we have a conformal symmetry in a Coulomb problem, which is probably interesting thing to know, because we can transport it from the Calogero side. Now we go to the gravity, non-trivial gravity background. And we take this metric. This is Euclidean ADS, or hyperbolic space, if you wish, in the older notation. It has some G tensor and some inverse metric tensor. And this is some alpha, which is interpreted here as a deformation parameter. But the constant curvature in the background in terms of alpha is written here. So I am in whatever dimension you wish. Okay. Note that this object is electric potential, which is correspond to the point charge sitting in the center of the symmetry. And so it is not just one standard Coulomb potential. It's deformed by alpha, you see here. And how it's deformed, it's, well, I will show that. But first of all, I say that if you go to the Hamiltonian, which corresponds to the motion of point particle in this background, It's just the standard one. You see that if you have a Hamiltonian particle moving in the curved background, so the Hamiltonian is given by inverse matrix contracted with momenta and by electric potential. So so far I didn't work out the magnetic examples, but it should be possible. So if you work it out, you obtain this formula. And you know that in n equals 3, V is repulsive Coulomb potential in the space of negative constant curvature, because if you apply the Laplace-Beltrami operator on this deformed Coulomb potential, you obtain the delta function. And now the problem which we ask, so we have a standard Coulomb problem and a hyperbolic Coulomb problem in the space of constant negative curvature with hyperbolic Coulomb potential. And we ask whether they are canonically equivalent, whether they are T-dual one to another. And they are. So is there some canonical transformation? It's written there. So the same story as before, that we have this x tilde and p tilde, and we like to see on the right-hand side just x and p, but we see some more complicated objects like psi and j and k, and we have to explain what they are. So m is simple, k is also quite simple, but j and psi need a new transparency. They actually, j is related to the psi by a composition of two maps. So psi is given in terms of p and x quite in a simple way. However, this map is much more involved, you know. But still, you appreciate they are just standard functions. There are no exotic functions. There are just, you know, functions which are at reach, you know, tangents, arctangent hyperbolic, and still, so you can cook up this canonical transformation using the standard function. Yeah. These are not obviously bijection, but if you work it out, they are. Of course, I did it. I worked it out, and they are bijections. One would not say it, but you know, but you have to. So they are, okay. Now, how these things this canonical transformation were obtained? So I'm in the middle of time, and I'm happy with that. So look, you start with some Hamiltonian, let's say Coulomb. You start with Hamiltonian, which is putative dual. Let's call it conformal. It's still the same letter, so conformal is CF maybe. And the idea is to map this to some intermediate system, like we would say the Drinfeld double, and this to this intermediate system by canonical transformation, and the result here is the same. No, yeah.
Conformal here means massless particles.
Conformal here, it means that the conformal group in 0 + 1 dimension is this, SL2R. It's just the conformal extension of simple translation, time translation, which are generated by Hamiltonian. Now, the scaling dimension in phase space has this generator, you know, Netter charge, if you wish. And it turns out that if you take this Calogero Hamiltonian, it has nice commutator or Poisson bracket, if you wish, with scaling dimension, which is multiple of Hamiltonian. I forgot which multiple it is, maybe -2. You know. And so this is one of the commutation relation of SL2R. And then if you complete, and this is the generator of special conformal transformations, x squared. And if you calculate the Poisson bracket, of those three objects, they close to the conformal group. And if you put the question differently, if you take this, and you look for Hamiltonian, you find Calogero Hamiltonian. So in this sense, this is a conformal theory. And so we must look for some intermediate model. And this intermediate model will be super integrable model. So we show that both Coulomb, it's known to be super integrable. For Calogero, I didn't know whether it was obtained somewhere, whether it's super integrable, but I showed that it's super integrable. So you take those two flash arrows and you compose them in this and then in inverse direction, and you obtain this canonical transformation, which I have shown you. Yes, you obtain this. So this object, which is complicated, is the composition of two simpler canonical transformations. And so let me now show that you could say now I take whatever two superintegrable models. When I show that they are superintegrable, then they are T-dual. This is not true. There is a whole zoological garden of superintegrable sigma models, and this is symbolized by this picture. But before I'm getting to this picture, you have basically, if you have two Hamiltonians which you suspect to be T-dual, you have to map them to the same window in this scheme in order they be T-dual. If they go to another window, they are not T-dual. But let me see what all this means. So now, what is the dynamical system? So you would say that you learned that in school. Not quite true. In very few textbooks, you find the truth, and in majority of textbooks you find the approximative truth. So dynamical system is of course phase space with a symplectic form and with a smooth function h, which is called Hamiltonian, and which generates evolution via the Poisson bracket. So far so good. But then we require that the flows generated by Hamiltonian must be complete. So they can be smoothly prolonged to both forward and backward infinities. If they are not, we don't buy such a system. We don't say it's dynamical system. And the reason for this precision is that if you don't have this precision, then the speak about integrable or superintegrable Hamiltonian system becomes empty. The Hamiltonian system must have this completeness in order to give a sound mathematical meaning to the notion of integrability or superintegrability. If you look at the many papers in physics about integrable model, they don't speak about completeness of the flow, and they still obtain some results. So actually, it may be by chance. The model which they studied, they have complete flows, but they didn't check it, and fortunately, they obtained the correct result. But if the flows are not complete, the story is empty. The integrability is a subtle notion, and if you don't ask complete flows, almost every system is integrable. So this is not so stringent quality of the dynamical system to be integrable if you don't put in the definition the complete flows. So what is the integrable dynamical system? It's a dynamical system which has one property, that if you take all functions of the phase space, it must exist a maximal abelian Poisson subalgebra. You know what it means, that if you take two functions in this subalgebra, the Poisson bracket must vanish. And this is maximal, that you add any other functions, it will not vanish. And then you require, and this is important, that each element of this Poisson algebra A generates a complete flow. So you don't recognize here in this story standard definition when somebody tells you that you have n commuting nether charges which are functionally independent. But I'm telling you that this is a brief way to say the same thing. You know? And then you have another definition which is quite funny to call it definition because almost triviality. You just take half plane. Take half plane. You run time here and the coordinate h here. You put a symplectic form on that. And this is your phase space. And then what is the dynamical system? For Hamiltonian, you just choose the coordinate h. And it turns out that it's a good integral system. What are the flows of this Hamiltonian? They are like that. They go from minus infinity to T infinity. We call it universal dynamical system in one dimension, and we are here. This is this half plane. Not every integrable dynamical system in one dimension is this. There are some others, half cylinders, for example, spheres, and that. But I worked to establish the example of T-duality with this case. So maybe there are some other examples, but I'm working in this case. So this I put as a definition. And now to construct examples of one-dimensional T-duality, I need just one function of P and X. Here it is for the Calogero Hamiltonian. And this function is a conjugated, canonically conjugated variable observable with respect to Hamiltonian. So you see T with H must be equal 1. You could call it time, but it's in the literature it's called tempus. The tempus is a function on the phase space. So what is the tempus here in this half plane? What is the function on this half plane which Poisson commutes with Hamiltonian to giving 1? It's T. It's just this big T. It's not small t. Small t is evolution parameter, is big T. So if you now calculate, so you have a bijection from this dynamical system, which is Calogero 1, to this universal y-dimensional system, which is half plane HT. And this is this bijection. You can check that this is a bijection. The best way to show it is by calculating the inverse canonical transformation. It's here. And without any surprise, if you interpret this tempus as time, those are just solution of Hamiltonian equation of motion of Calogero models. So you have two possibilities. When somebody tells you solve Calogero models, you find the solution by solving Hamiltonian equation, or you find the tempus. Its relation. Hamilton Jacobi helps you to find tempus easily. Yes. But this tempus is not much used in the literature, but it's used sometimes. And the reason that sometimes the solution of Hamiltonian equation they require some special function, like even the Kepler problem. It cannot be solved in terms of elementary function because the way how you are on the ellipse, the angle depends on time. This is a complicated function. But if you go to inverse canonical transformation for Kepler problem, then the elementary functions are sufficient. So basically, all technical details is that you take some Hamiltonian P and Q, you construct some other function which realizes the symplectomorphism to this universal system, HAT. And so, for example, I take two Calogero models with different coupling constant. One, I have tempus with J and G tilde. So I realize, first I realize the transformation from Calogero to this universal half-dimensional model. And then from different Calogero with different coupling constant to the same model, and I relate them. And I obtain this canonical transformation, which was in the one of the first transparencies. Here it is. So I have this property. So in one dimension, I go through this one-dimensional model. In high dimension, I don't have any such universal model, so I have to be much more clever to get examples. So I give you a definition of superintegral system. Again, this is not the standard definition. I'm not quite sure that it's totally the same as is a standard definition, which is quite complicated. But morally, it's the same. I'm pretty sure it's almost the same. But it's much easier to understand. Just let me say, the idea is that if I have in a higher dimension two Hamiltonian and I want to know whether they are T-dual one to another, I need some intermediate system. And this intermediate system will have, for me, it will be something canonical. It will be superintegrable and with a maximal symmetry. So what all this means? So first of all, direct product of dynamical system is defined in this way. This should not be a big deal. No? That you add symplectic forms, you add Hamiltonians, and you take direct product of manifolds of phase spaces. Then you define something which sounds completely useful. It's static dynamical system. This is just a triple where you have phase space, symplectic form, and zero Hamiltonian. You have no evolution. It's just a symplectic manifold. But why is that important? Because superintegrable dynamical system is a direct product of an integrable system with a static system. And so if you have, for example, superintegrable system in n dimension, it may have a situation that it's just a direct product of one-dimensional system times n minus one-dimensional static system. And this is Coulomb. For example, Coulomb problem has exactly this property that it's essentially one-dimensional because all the rest you can arrange in such a way that you get the static dynamical system where there is no evolution. And so you have a bit of such a scheme if you take this. Here there are different symplectic manifolds. This is potato, this is ananas, this is I don't know which, this is cat, you know. Here are different one-dimensional integrable systems, cylinder, half-plane, sphere. And now I start with some Hamiltonian which is of interest for me, for example, hyperbolic Coulomb. And it turns out that it's here. That it's direct product of half-plane with ananas. And now I take ordinary Coulomb, and I find out that it's also superintegrable of the form half-plane times ananas. So they are T-dual to each other. If I take some other, for example, instead of ananas, I take cat as a dream, for example, Heisenberg double, then I may take one model to get here, another model to get there, and there is no T-duality. Yes?
You allow this static dynamical systems to be as generic as possible, but I guess it can also be
That's
if it is necessary to have superintegrability,
yeah.
or it would be enough to have just integrability. Then the static dynamical system is just something trivial. We could have canonical transformation also in that case.
I'm not sure I understand. You know, if you have superintegrable system, they fall in such a matrix. On the horizontal line, you put those static system, which can be whatever symplectic manifold you wish.
Can it be trivial? Can it be a point?
Yes.
Okay.
If you have a point, you get back to one-dimensional example which I have constructed before.
Yeah, because that.
But if you want to get to a high-dimensional example, it cannot be point. So I took the cotangent bundle of a sphere. So I start for this manifold, for this ananas, I am taking the cotangent bundle of a sphere because this guarantees me Killing symmetry of the background. Okay. And here I'm taking this half plane. But please, not every centrally symmetric system is superintegrable. No, there is some condition which is, maybe I come back to that, but this Fratkin, you know, maybe it comes as a surprise for you, Arkady, he was your teacher now. Fratkin studied condition when a centrally symmetric background is superintegrable. And he found some mechanical condition that you need some observable which should be interpreted at the quantum level as a S matrix. And it should have a Poisson bracket with Hamiltonian and with two distinguished vectors of the particular form. And if this is the case, then you establish that this system is superintegrable and it falls to this window of the matrix. It means it's half plane times ananas, which is cotangent bundle of S and minor. So we can thank the Fratkin that we have this criterion, and the only thing to do is to find out psi which verifies this Poisson bracket. Okay, and that's more or less all, because in the literature you can find that this Fratkin criterion can be solved in the hyperbolic background. You know, so actually people in the literature, they don't specify tempus. I had to calculate it. It's not that I just took their formula and the brick and use. I have to complete in some way. I had to invert the canonical transformation on one side which they obtained. But basically the system is that once you take two Hamiltonians like ordinary Coulomb and hyperbolic Coulomb, you solve the Fratkin criterion, you establish canonical transformation to this superintegrable system where you have half plane and static cotangent bundle of Sn minus 1. Then it's enough to invert this transformation to compose it. One transformation composed with inverted is a canonical transformation which realizes the T-duality. And the question about the bijection is actually a question already which can be solved here. If this is a bijection and if this is a bijection, so the composed map is also bijection. So when you ask me a question where all this is bijection, I didn't check it directly. I checked it in 2 steps, you see. Okay. Now, conclusions and outlook. I think I'm approaching, it's 52 minutes, okay. So I take a dynamical system which is symmetric. In this particular case, it is spherically symmetric, but it could have been Poisson-Lie symmetric too. Then I check that it's superintegrable, that the Fratkin criterion is fulfilled. And then I know that this system, you know, every system which has the same property is superintegrable and symmetric is T-dual to it. Okay. So many superintegrable systems were constructed so far. I'm sure that many of them, they fit in this window. I found 3 of them but I believe that there are some others. So it seems that to construct a T-duality example in a point particle case is much easier than in the string case. And of course, there are some other examples, you know, which are in some other windows. This could be Heisenberg double, this could be sphere, this could be half cylinder, etc. But the challenge now is to see whether all this structure can be quantized. You know, in string theory, this is a big problem, you know. The Poisson-Lie T-duality and Umami T-duality is a classical object. We don't know how to quantize that. We have some partial result about quantum T-duality, but here it should be under the complete technical control to see whether T-duality takes place also at the quantum level, or there is some anomaly of T-duality. Of course, this should be simple, but not that simple, because if you have seen those canonical transformations, they are very cumbersome, you know, and to directly quantize such an object, this could not work. We can find other way probably to quantize this picture, you know, to find the unitary transformation his side and that side and compose them, something like that. But I'm eager to work it out because I just want to know whether the T-duality, which relates in quite, to my point, improbable way, different Hamiltonian, whether they can do it also at the quantum level, you know. You take a Schrödinger operator with 1 over r and 1 over r squared, and you find unitary transformation which relate them. So for me it's not evident, but it may work. So thank you for your attention.
Thank you. So any questions?
What about boundary conditions? Quantum mechanics, there are also other conditions like
normalization, wave function. Looks like they'll
I don't know
completely disconnect.
what's happened in quantum mechanics. First, you remark that by choosing this half plane, I'm concentrating on the dynamical system which have only infinite motion. So essentially S matrix, they have S matrix. This S matrix.
That excludes in particular, if you have a metric which is not geodesically complete, that will not be the case.
Yeah, if you have
Any metric like Schwarz.
any metric which is not geodesically complete, probably will not give you the complete flows, you know. And I agree with you that there may be some metrics which are not geodesically complete, but what I think what may happen that if you may take ugly metric and you may find that it's locally T-dual to some nice metric which have this geodesical completion. This might be, for example, you solve Schwarzschild singularity in this way, you know. But this is, you know, totally fantasy. But this T-duality bring one ugly system to the nicer one, you know. Already some dynamical symmetries, you know, which are hidden in some picture, in T-dual picture, they may become manifest, you know.
Is there any analog of what could be called T-folds, like, you know, when you glue together?
Yeah, there should be some analog of that. Actually, you know, those canonical transformations would just relate the patches of the phase spaces, you know, in some way. So it should be analog of T-folds. Yeah. Yes.
So at the beginning you were describing some sigma model on some targets. When we do normal T-duality, the condition for dualization translates to some isometric, non-isometric, some condition on the geometry. Is there a statement here at the geometric level?
There is a statement which goes other way around. The statement is that it's similar. Here, if you have killing symmetry, rotational symmetry, so this enhances your chance to have T-dual. You need more than that. You need Fradkin criterion. So the symmetry plus Fradkin criterion guarantees you existence of T-dual.
And can that Fradkin criteria be stated in a sort of geometric, natural way?
I think that I'm pretty sure that when examples of quantum point-particle T-duality are worked out, this Fradkin psi will play the role of S-matrix. I have this feeling. You know, so this would have this interpretation, some physical interpretation, I believe. Yes.
Is there any chance you can extend your Calogero maps to more particles?
Yes. Well, Calogero started this 1 over x case, and then his basic contribution, why it's because so famous, that he coupled several particles of this type. But this goes, for me, outside from the geometrical interpretation of the background. If you have n Calogero particle, this is a honest dynamical system, but it does not correspond to the motion of single particle in some geometrical background. Like, you know, T-duality, we study motion of single string in some geometrical background. So here we study a particle, but it's pretty the case if you couple several Calogero particles, still this system is integrable. And if you choose, well, the Hamiltonian, it may be even super-integrable, you know. In general, super-integrable system is integrable times static. So all depends what is the static, you know, and what is this integrable. Yes, so you can go in this direction, but we get out from T-duality. We are losing this geometric interpretation.
But if I was just interested to see if two different Calogero systems with different coupling constants are canonically related, you say the answer might be yes, even for multi-particles.
They are, even of whatever dimension, this I have shown. I didn't tell you, yeah, you are right. I have shown it in one dimension, but it's true in whatever dimension. Because Calogero model is spherically symmetric and super-integrable. So I didn't state it in this way, but if you change coupling constant in Calogero from weak to strong, still it's dynamically equivalent. Okay.
Is it correct to say that the difficult statement is the bijection, because provided the phase space is of the same dimension, a map exists because of Liouville theorem?
Well, already to establish that you have a dynamical system, that it's super integrable, that it has somewhere hidden a static part which does not move, it's already a big deal. You know, there are constantly papers. Recently I have seen a paper that the guy said, I obtained 66 new super integrable system, you know, with some Hamiltonian and that. It's a big deal, you know, the canonical transformation which those people construct are horrific, you know, that. But they are under control. So yes, you have to do a lot of analytical work to establish bijection. If you look at the Ruyssenar's papers about Ruyssenar model, 100 pages of hard analytical work to show that one map is bijection, you know. But you can use it in this because those people did it for you, that this is bijection. You just compose 2-day bijection and you say it's T-dual. So, yeah.
Sorry, Stirat, is there counterexamples when, suppose, this Fradkin criterion holds for spherically symmetric systems, right? If it is non-spherically symmetric, you say that there wouldn't be canonical bijection.
No, they would not be Fradkin criterion, but it would be something else. You can study, that this is a honest question, this thing, for example. Somebody gives you phase space with px coordinates, gives you Hamiltonian, and he asks, is there a canonical transformation to half plane times the Heisenberg double?
Yeah.
And such questions are remarkably difficult to answer. So there is whole literature in super-integrable models that they have special journals, those people, and that. But they have never asked question whether two different dynamical systems, they fall in the same class, you know. And this is a question about T-duality, essentially. So, of course, there may be examples of T-duality which are not super-integrable, I don't know. But
yeah,
super-integrability helps a lot to construct the example of T-duality.
Yeah, that was my second part. Like,
Yeah,
if second part was, if I go to high dimensions apart from your one-dimensional, and can there be a canonical transformation still existent for non-super integrable? Like, just I think Ricardo was asking, like, integrable.
I don't know. You know, everybody has some personal evolution. So 2 years ago, I was happy to cook out the canonical transformations, and then I had an idea. Why not to look in the literature about this idea of super integrability came later, and then I realized that you can produce a lot of examples, not just artificial, but Coulomb example is the center of physics, you know, and still it turns out that Coulomb is T-dual Calogero, and it's T-dual Euclidean ADS, and that are, so there's some web of dualities at the level, and I suspect that even in string side, this we can get out from the Drinfeld double, because I personally started with Drinfeld double in point particle case, and then I realized that you can get out of it. So probably in string theory also this could be a path to follow, to look for super integrable sigma models, you know. And if you establish the two sigma models, I honestly believe that maybe Young-Baxter model and principal chiral model are both super integrable, and that they are in fact T-dual, and this T-duality would not be Poissonly, it will be some new T-duality. So I honestly believe that this is the case.
Can you maybe clarify what is the difference between a T-duality transformation and a time-independent symmetry transformation?
And
Time-independent symmetry transformation.
Well, time-independent symmetry transformation is a canonical transformation which is of point type, it's called. This is
No, that's not true. It's not of point type.
So
It's just a general canonical transformation which preserves the form.
you speak about dynamical symmetry or symmetry of configuration space.
Symmetry of a mechanical system, a symmetry which maps solution to equations of motion to another solution.
It preserves Hamiltonian.
Yes. So if it's time independent, then it preserves the form of the Hamiltonian.
But that's okay. I understand your point. I understand your definition of symmetry. It's dynamical symmetry. It's not kinemical one. And I'm telling you, all functions living on this ananas commute with your Hamiltonian. They are generators of symmetries, of dynamical symmetries.
Sure. Yeah, Poisson commute.
Yes.
Yeah.
So they are generators of symmetry. This static system is a system where you put all nether charges. They live there in their bubble. This is the interpretation of this static dynamical system. This is the system which is, those are function of integral of motions, which via Poisson bracket generate those symmetries.
Yeah. Maybe a naive question. If you have an incomplete Hamiltonian flow, why can't you just remove bad points from the phase space?
You do.
Okay.
That's what you do. Sometimes you can do, and sometimes you cannot. When, for example, in Kepler, attractive Kepler, this is incomplete because you can fall down to the sun. But you can remove from the phase space all points where angular momentum is 0. And since angular momentum is integral of motion, this is a consistent removing. And so what remains is a dynamical system which is complete. That's, you play this game, actually.
So which paper of Fradkin you're referring to?
I don't know, because I found this Fradkin criterion in a paper of Ragnisko, and he refers to Fradkin, so I can find it for you. Okay?
Okay, I see.
You know, this is the propagation of citation. You know, so.
See no further questions, so maybe let's thank Tirad again
Okay.
for the nice talk. And we resume at 11:15. So it's my pleasure to introduce the next speaker, Sylvain Lacroix from ETH Zurich, who will be telling us about integrable sigma models at RG fixed points, quantizations at affine models.
So yeah, thanks, and let me start by thanking the organizer for giving me this opportunity to talk here today, and for putting up the conference. It's quite a pleasure to be here and finally be able to discuss with everyone. And so what I would like to present today is some work in collaboration with Gleb Kotusov, which is also here at the conference, and Jörg Teschner, about integrable sigma models at RG fixed point, and in particular their quantization using what are called affine Godin models. So an introduction, I'll be talking about sigma model, which are two-dimensional field theories whose various application I think I don't need to advertise for this audience. And more precisely, I'll be talking about integrable sigma models, which are the one for which there is infinitely many conserved charges in involution at the classical level. And since the 70s, we have a growing list of examples of such integrable sigma models, for instance, including the integrable deformations we've heard a lot about. And this raised the question of whether there is some common origin, a common theory that describes the integrability of all of these models, or at least most of them. And there's actually several answers to that, which are all related in various ways, including, for instance, what are called 4D Chern-Simons theory, E-models. And here I will take a rather algebraic approach, which goes under the name of affine Godin models. And these in particular have been used a lot to explore the panorama of classical integrable sigma models and construct new examples of these theories in a systematic way. But today I'd like to talk about another potential application, which goes more in the direction of quantization. So the question is the following: if I have a certain sigma model which is integrable at the classical level, can we prove its integrability at the quantum level from first principles? So really in the sense of I will look at the algebra of observables of this quantum field theory and build an infinite number of charges that commute, and we would like even also to diagonalize it. And this is a famously hard question, but here to make it already a bit simpler, the approach that I will follow is I will start by looking at the integrable structure of the conformal points of these spheres. And the reason for that is that the formalism of two-dimensional CFTs, it actually gives us quite a lot of control and quite a lot of mathematical rigor. For instance, there's less or no UV divergences in this theory. There's the decomposition into left and right moving fields, which in particular quantize to what I call vertex operator algebras, which gives us the right framework to even ask about the question of computing these charges that commute. And so in this context, the main goal of our paper was to explore the applications of affine Godin models to the quantization of integrable sigma models at their conformal points. And in the paper and in this talk, I will actually focus mostly on one example, which I'll call the Klimschik model, and which is also called the Bion-Baxter model, which is a specific example of an integrable sigma model. So my plan will be the following. So let me start by saying that although in the end I want to go towards quantization, I think starting directly with the quantum level would be maybe not too pedagogical. So I will actually stay a lot at the classical level to kind of prepare everything we need to in the end go towards quantization. And I will start then by a general reminder about integrable field theories in the Lax formalism. Then I will define affine Godin model at the classical level, and then relate them to integrable sigma models using the notion of relativistic realization. And in particular here, I will use this example of the Klimschik model. And then I will look at the conformal limits of this theory in the UV and find and describe in particular its chiral and integrable structures. And this will allow us then in the end to go towards the quantization of these theories. But let me start with general reminder about integrable field theory through the Lax formalism. So I'll consider a 2D field theory with some fields phi I tx, and I take the space variable x to be in the cycle with periodic boundary conditions for the fields. And the key ingredient for the integrability is the existence of a Lax connection, which is a pair of two matrices L and M that are built from the fields and some auxiliary complex parameter Z, the spectral parameter, such that the equation of motions for the field theory can be recast in the form of a zero curvature equation in terms of L and M. Then if I add this, I consider the monodromy matrix of the spatial component L, the Lax matrix, around my cycle, defined as a parflexion exponential. And a nice result is because of the dynamic of L as the zero curvature equation, the traces of powers of the monodromy in some representation of the group are a conserved quantity. And also because we have the dependence on the auxiliary spectral parameter Z, I can expand in powers of Z and get this way an infinite number of such quantities. Now, to really get integrability, we would like the concept quantities to be in involution, so to Poisson commute with respect to the Hamiltonian structure of the model. And so we need to study the Poisson bracket of the Q's, which are built from T and themselves built from L. So in the end, we need to look at the Poisson bracket of L with itself, which will lead to the notion of Maillet bracket. So to describe it, I will use the tensorial notation. So if A is a matrix, then A1 will denote A tensor identity, and similarly here for B2. And then I will decompose my Lax matrix L in a choice of basis of my Lie algebra and look at its components. And now what we can do is, using tensorial notation, I can basically encode all the Poisson bracket between the different entries of the Lax matrix at different values of the spectral parameter and of the space variable into one unique object by contracting them with the basis T8 tensor TB. And so this is then an element of G tensor G that encodes all of my Poisson bracket. And just a remark here, because now I'm working with Poisson brackets, so in the Hamiltonian formalism, it means that I'm working with a fixed time. And so now I will remove all the time dependence in my fields. And now the question is there a sufficient condition on these brackets that ensures that the charges extracted from the monodromy of L are in involution? And well, there's several actually conditions that ensure that. Here I will take a rather general one, which was found by Maillet, and which is called a non-neutralocal bracket, and which looks as follows here. So there's a term proportional to the Dirac distribution of the space variable, which is what we typically expect in the Poisson bracket of fields in an Hamiltonian field theory. And this term contains then a commutator of the Lax matrix with an object called the R matrix, which is an element of G tensor G, which depends on the two spectral parameters. And then there's also what we call the non-neutralocal term, which is the derivative of delta here, which is also controlled by this R matrix. And the result is that if L satisfies this bracket, then the charges extracted from the monodromy are all Poisson commuting, and we really get complete integrability in the Hamiltonian sense. Now, two quick additional remarks on the Lax connection that I will need to use. Well, so far I used the space-time variable T and X, but because I will be looking at a relativistic model, it will be actually quite useful to use light cone coordinate instead, T plus minus X and the corresponding derivative, in which case I can look at the zero curvature equation for the Lax connection in the light code form, which is the one I will use then throughout the talk now. And the last small comment is that the Lax connection in general is not unique. I can always take my connection and conjugate it by some function valued in the group, and I get another connection which then also satisfies the zero curvature equation if the initial one did. So I don't have a unique choice of Lax connection, but then all the charges I extract from traces of the monodromy, they're independent of these terms. Okay, so after this general reminder, I would like to then use this to define a particular class of classical integrable field theory, which are called affine Godin models. So to fix the notation here, G will be a simple Lie algebra with a certain basis TA, structure constants describing the commutation relation, and eta will be basically the minus the billionaire trace in some choice of representation, which is then a non-degenerate invariant billionaire form on the algebra, which is just proportional to the killing form. And here I take a minus so that it's positive if the Lie algebra is compact. And because it's non-degenerate, I can invert it, which I denote by raising the indices, and then I will use eta to freely raise and lower indices in my Lie algebra. And in this context, then the classical affine Godin model is defined as a certain Hamiltonian field theory, whose fundamental fields are what we call Cox-Moody currents. So precisely here I take n Cox-Moody currents, which are then n fields valued in the Lie algebra, or more precisely the complexified Lie algebra. And in general, I should have reality conditions to ensure that the end results of my theory are real, but I won't enter so much into that here today. The main property that this Cox-Moody current should satisfy is they should have a specific Poisson bracket defining then the Hamiltonian structure of our model, which if I decompose them in components in a basis, then look as follows. So there's the delta term here with some basically commutation relation of my Lie algebra here. And there's a term proportional to delta prime and a certain constant LR, which is a coefficient that we call the level, and which here then will be part of the defining parameters of my affine Godin model. And note also that there's a Kronecker delta here in front, which means that if I have the Cox-Moody current with different indices, they simply Poisson commute their independent observables. Now, key ingredient in the definition of the Godin model are the so-called Godin-lax matrix and twist function, which are certain functions of the spectral parameter z with poles at n specific point, which we call the punctures zr. And so more precisely, we have as many points as there are Cox-Moody currents, and the corresponding residue at zr in the Godin-lax matrix gamma will be the corresponding then Cox-Moody current, and similarly in the twist function, the residue will be the corresponding level. So now, in particular, inside of my twist function, I have the data of all the parameters defining my affine Godin model, the punctures zr and the levels lr. And then inside of my Godin-lax matrix, I have access to all the fundamental fields defining my field. And now what I would like to explain is how from there we can naturally construct an integrable structure in a sense of Poisson commuting charges built from these Cox-Moody currents. And so for that, I will use the Lax formalism that I just recalled. And in particular, we will define the Lax matrix of the theory as almost being the Godin-Lax matrix gamma, which is divided by the twist function phi. So this is a specific function of z, which is a linear combination of the Cox-Moody current. And because I know the Poisson bracket of the Cox-Moody current, from there I can compute the Poisson bracket of L. And after a small computation, I find that it exactly satisfies the Mayer bracket, as I presented before, with a specific choice of the R matrix, which is given by this expression here. So C here is the split quadratic Casimir, so an element of G tensor G, which is built from the billionaire form. And then there is the twist function appearing here, depending on the second spectral parameter, then keep the information about the levels of my Cox-Moody current. And so now, in particular, the consequence of that is because I have a Lax matrix satisfying a Mayer bracket, then I can look at the monodromy and I can extract an infinite family of charges in involution for the monodromy of L, which in general are non-local charges because they're built as parforwarded from the parforwarded exponential. In addition to these non-local charges, there are also local ones, which were built in this paper, building from some result of Evans, Hassan, McCain, Montaigne. And so they take the following form here. So they're labeled by two type of indices. So one index that just grows with the number of Cox-Moody currents. So if I have n Cox-Moody current, I will have n minus 2 families of local charges labeled by some I. And then for a fixed I have an infinite number of charges labeled by their degree p, which take value in a certain set of positive number e, which is infinite but depend on the Lie algebra that I choose. But it always starts at p equal 2, meaning that I always start with some quadratic charge, and then I can have higher degree 1 cubic quartic depending on the choice of my Lie algebra. And very quickly, the form of the charges is as follows. So they're local in the sense that they're integral over the space variable of a local density, which here is simply built as a polynomial of degree p in my Cox-Moody current components. And these components, they are contracted with some well-chosen invariant tensor on my Lie algebra for the Lie algebra indices. And then the different Cox-Moody currents, they're mixed by some well-chosen choice of coefficients in front of it that depends on the parameters of my Godin model, so the punctures and the level. And all these objects should be very well chosen in a very specific way, which ensures that in the end, from the Poisson bracket of the Cox-Moody current, we can show that all these charges, they Poisson commute one way or another. And so we also get an infinite family of local charges in involution from the construction. Now we can actually show that the local charges turns out to Poisson commute with the non-local ones as well. So to summarize the whole construction so far, what we did is we just built a whole infinite family of Poisson commuting charges built from the Cox-Moody current JRX, either in a non-local or in a local way, and which all Poisson commute and which depend on a certain number of parameters, ZR and LR. And this is what I will refer as being the integrable structure of AGMs. It's this infinite number of charges that commute. Yeah.
Can I ask a question? Well, somehow we are taught to believe that all the non-local charge, all what comes from Lax matrix should be complete in some sense, that these non-local charges should cover everything, so those locals can be in principle expressed?
Actually, no. And that we can show, actually, there's an argument, for instance, that the charges that are in the monodromy, in the end, they will have no spin, while here these have
they do have
the spin, and so they cannot come from the monodromy. They're just independent construction. Yeah.
Okay.
It's quite different than some other standard field theory, like maybe the KDV, let's say, where the local charges are
it's
extracted
just to
from,
point out whether the direction of superintegrability, you know, you have more charges.
Yeah,
than
we have
the-
more charges than what the Lax connection simply gives us, yes. Yeah.
But in a sense, the existence at the quantum level of these local charges is actually the important one for quantum integrability, right?
Sorry, could you repeat?
The existence of these ones at the quantum level is what's important for quantum integrability.
Yeah, for
to
instance,
exist.
actually, if we want to apply the argument of Park and so on, and the factorization of the ace matrix, that would typically use higher spin. Although I think there are also now some results, I think maybe from Florian Lobert, about how non-local charges can also imply factorization. But indeed, I think the initial argument would be typically using some higher spins ones. Yeah.
And sorry, just to comment, there's some story that the bottom brackets of the monogamy itself are not well defined.
Yeah, so there's the problem, what is called the problem of non-neutral locality, which is due to the presence of a delta prime in the Bayer bracket, which puts some ambiguities in the Poisson bracket of the monodromy itself. So this is actually quite a problem, in particular in the direction of quantization. Let me just say that actually, in order to prove that the invariant of the monodromy, so if you take traces of the monodromy, this then actually you can show in the end without so problem of ambiguity is that this is really Poisson commute. It's more to define the Poisson bracket of the entries of the monodromy, maybe like to have some kind of Young-Baxter equation or something like that, that there is a problem. Another remark here is that the local charges, they don't suffer any of these problems, for instance. Okay, then if there are no more questions, then let me go on. So, well, we just defined this integrable structure of local and non-local charges. Now, just one important property for later of these is that in general they possess a certain gauge symmetry. There will be some kind of local redundancy, which is that if I take the following local transformation of my fundamental fields, of my Kac-Moody current, where H is some arbitrary function valued in the group, so I have the adjoint action on and then some derivative, like in a transformation of a gauge field, then if I take this transformation, I can look at how the Lax matrix transform. It's a linear combination of the JR, and I find exactly the transformation and the conjugacy of the spatial part of the Lax connection, right? So what we see is that this gauge symmetry here is equivalent to a conjugacy of the Lax matrix by H, which is independent of the spectral parameter. And this has in particular an important consequence, which is that the non-local charges that we extract from L, from the monodromy of L, remember that they're independent on the conjugacy of the Lax connection, meaning in particular that here they're independent of this gauge symmetry, this particular local transformation of the fields. And actually we can show that the local charges are invariant as well, meaning that in the end the whole integrable structure of affine Godin model possesses this gauge symmetry. All degrees of freedom are not physical, there is some kind of local redundancy. Okay, so now that I have defined these general affine Godin models, what I would like to do is make the link of this with integrable sigma models through the notion of relativistic realizations. So the idea is that so far what I presented is what I would call the abstract or the formal affine Godin model, which is really this theory with fundamental fields are the Kac-Moody currents. So the phase space is just the configuration of these currents equipped with the Kac-Moody bracket. Now to consider a realization, what we'll do is we'll take a maybe slightly more standard phase space for an Hamiltonian field theory, which is given by canonical fields in a certain cotangent bundle T star Q, by which I mean something quite simple actually, is I have some coordinate fields phi I x living in some space Q, and then I have the corresponding conjugate momenta pi I, which lives in this then T star part, and they're equipped with the canonical brackets of Hamiltonian field theory, so pi with phi is a Dirac distribution, and a Kronecker delta, and then all the rest is 0. And now to get a realization, I will suppose that there are some well-chosen combination, JRX, of these canonical fields and their derivative, such that the canonical bracket for phi and pi implies that this specific combination satisfies the Kac-Moody bracket. So I realize the Kac-Moody bracket in terms of canonical fields, and because this Kac-Moody bracket is at the basis of the whole construction of the affine Godin model, in particular the integrable structure, then I can transfer all this construction to this new phase space. And in particular now I get a bunch of charges in involution which are now built from the canonical fields in T star Q, because they're built from JR, but JR is itself now a composite field in terms of the canonical fields. Now, let me say that so far I actually focused only on kinematical aspect, in a sense that I have a certain phase space, so now which is given by these canonical fields in T star Q, and I built an infinite family of charges in involution in there, which I call Z. If now I really want to have a 2D integrable field theory from this construction, the last step that I need to do is I need to choose a dynamic. I need to say what is my time evolution, which I do in the standard way by choosing an Hamiltonian H, whose Poisson bracket will define the time derivative. And I'll take H here to be an involution to Poisson commute with the element of Z, so that by construction the element of Z are conserved, and they're also in involution, so the theory is then automatically integrable by construction. And a natural choice to have H which Poisson commute with Z is to take H inside of Z itself. And here I'll actually take a very specific choice of that, which is I'll take H to be a linear combination of my quadratic local charges. So remember that I had these n-2 families of local charges which have higher and higher degree, and they always start at quadratic, and here I take my Hamiltonian to be a linear combination of those with some coefficients Si. And that defines then for me that time evolution, and now I really get a 2D field theory with variable T and X. In particular, now that I have T and X, I can ask about the space-time symmetries of this theory. And for instance, about relativistic invariance, so Lorentz invariance under the boost of T and X. And actually, under some technical assumption, we find actually that there is a very simple criteria for this relativistic invariance, which is that the coefficients Si that are defining the Hamiltonian, so the time evolution, should all square to 1. So they should be either +1 or minus. Yeah.
Can you somehow strengthen this result and ask invariance with a special conformal group, for example?
So for conformality, it turns out that classically these are always conformal.
I see. So, but so you can construct not just H, but all Virasoro generator.
Classically, yes.
Yes.
Because classically, we have actually access to all the energy momentum tensor. And for instance, we can show that it's always traceless. And then we ask about symmetric, and that's what gives us the condition for relativistic invariance, for instance.
Okay.
So from there, by looking at the modes of T, we could extract all the Virasoro generators. And so with this simple condition, what I get is that, well, realizing my currents in some canonical fields in T star Q, defining the Hamiltonian, and then imposing this simple condition for relativistic invariance, I get a systematic construction of a relativistic 2D integrable field theory. And with that, I can actually get a whole zoo of integrable field theories just by varying the affine Godin model I start with, varying the type of realizations I take, and so on. And in particular, in all of there, I will find a lot of integrable sigma models, which is what I mentioned in the introduction, that this has been used a lot to explore the panorama of these integrable sigma models, and in particular, recover some old ones and find some new ones. And now I would like to show a specific example of this by recovering a specific integrable model, the Klimschik model. And for that, I need to first specify what is the affine Godin model I start with. And here I will take a affine Godin model with 4 punctures, Z1 up to Z4. And here I choose a specific choice for these punctures in terms of 2 parameters, epsilon1 and epsilon2. So here's the formula. It's maybe a bit complicated, but actually the details do not really matter. I simply take this choice so that in the end it makes some of the equations later quite simpler. And then, so it means that my twist function then will have poles at these ZRs here, and then I choose that the rest of my twist functions simply look like this. And here I have an additional parameter k that goes into there, which is just a global parameter. And now I define my twist function, so I define all the parameters of my affine Godin model, the punctures, and the levels which can be extracted as residues of this function phi. So now if I have 4 punctures, it means I have 4 associated Kac-Moody currents, J1 up to J4, and now I want to realize them to get a model. And what I will do here is I will realize them in terms of canonical fields in a cotangent bundle of 2 copies of the Lie group. So here the idea is that if I have canonical fields in T star G, there is an explicit formula to build from there a pair of Kac-Moody currents. The formula is really explicit, but I won't give it because it would require introducing a few notations. But now I just take 2 independent copies of this construction, which is now then in 2 copies then of T star G. And I get then 4 Kac-Moody current from there. And by construction, then my my realization of my Godin model will be then an Hamiltonian field theory in T star of G cross G, which means that if I go to the Lagrangian formulation, I will eliminate the canonical momenta, so basically I will get rid of T star here, and I will get a Lagrangian model on G cross G, which is then described by two fields valued in the group, which I will call here G1Tx and G2Tx. And I remember also that there was this gauge symmetry in the affine Godin model, so there was some kind of local redundancy. And for this choice of realization, one can prove that it acts on the fields G1 and G2 simply by right diagonal multiplication. So in the end, the real physical model that I get is an integrable model on G cross G, quotiented by the diagonal action of G, which I can identify simply as G itself. And one way of doing this identification is I take G1, G2 inverse, which of course then is because of this transformation, this is gauge invariant. So these are real physical degrees of freedom of my model. And now I will skip all the details, but if you do all this construction, you take the Hamiltonian, you plug it in the formula of the, coming from Godin, you do the inverse Legendre transform to go to the Lagrangian, express everything in terms of the gauge invariant field, you end up with this thing here. So before I talk about the interpretation and what identify this model, let me explain what are the ingredients in there. So we see that we have actually a sigma model form with the current G inverse D plus G and G inverse D minus G, which are contracted through the trace, so through our billionaire form on the Lie algebra. And in the middle, we insert some inverted operator, which is built from two types of objects. So I have my parameters epsilon1 and epsilon2. And actually, the reason I took this rather complicated expressions for the punctures was to make, in the end, the action as simple as possible. And then in front of these, I have some operators, R and Rg. So R is simply the Drinfeld-Jimbo R matrix. So it's a linear operator on the complexified Lie algebra, which we also saw, for instance, yesterday in a talk of Fiona, for instance, which act as 0 on the Cartan subalgebra and as plus minus on the nilpotent generators. And then Rg is simply R decorated by some adjoint action of the group valued field. And now some of you might recognize actually this sigma model. It turns out to be a sigma model which was quite well known before, and which is the Klimschik or Bayern-Baxter model, which was introduced by Stirat-Klimschik in 2008, and which was introduced as a particular two-parameter deformation of the principal Carroll model that correspond to the case epsilon1, epsilon2 equals 0, where we have just G inverse dg, G inverse dg, which is a famous integrable sigma model on the group. And well, this particular model, it was proven also that it was integrable, that, for instance, there exists a lax connection. And from our point of view here, because we recovered it from an affine Godin model, then it should also be integrable automatically. And for instance, there should be a lax connection that comes from the affine Godin model construction. And if we do the computation of what it is, we find that it's the same as the one found by Klimschik, actually equivalent, gauge equivalent to the one that was found. And in addition to the lax connection, we also have the local charges. So these, I think, were not known explicitly before for this Bayern-Baxter model, but they turn out to be deformation of some charges that were found by Evans, Hassan, McCain, Montaigne for the case of the PCM. So to summarize, what we see is that the Klimschik model is then a certain relativistic realization of a specific affine Godin model with 4 punctures. I make a very specific choice of punctures, a specific choice of realization. I turn on the machinery, and in the end I get this model, and I recover some of the known features of this model that were found before. Yes?
As you showed, of course, there's the affine quantum group symmetries that come from the non-local charges. Is there an algebraic understanding of what this deformation is on the higher spin charges?
How the...
yeah, what this deformation of... Is there a charge algebra of these
so I think so
local higher spin charges?
The local higher spin charges, they will be invariant, I think, under these affine QD-form symmetry in general. So actually, I think the affine symmetry, it was found only with a case where there is only one deformation, probably explicitly done. Probably it should be the case that there is 2 of them here, but so far I'm not sure it has been proven. But I would expect that the local charges are just simply commuting with all the generators of this. Okay, so, well, so far you might have remarked that I have no nothing about conformal limits, which was part of my, about the RG fixed point, which was part of my title. And so now in the second part, second half of this talk, I would like to then describe the conformal limit of this model, more precisely the UV limit, and describe its chiral and integrable structures. So far I've seen the Klemschik model as a classical field theory with 3 parameters, k epsilon 1, epsilon 2. Now if we look at this quantization, we'll encounter UV divergences as usual, which we need to treat by adding counterterms, which effectively tells us that our parameters will become dependent on the energy scale mu of the renormalization group. And this dependence can be described by the one-loop RG flow, which was found in this paper. So there are some proportionality coefficients here, which I don't put because they're not so important. This is one loop, so it's order 1 in H bar, and they should be then in general higher order correction, of course. And what's mostly important for us is that it's proportional to this coefficient xi squared, which is just a specific combination of my deformation parameters. And now let me just make an observation, which is, well, we've seen already the Bion-Baxter model yesterday in Dan's talk, but actually here I'm using a slightly different reality condition regime for the parameters, which changes a few things here, in particular a few signs. And in particular, this has an important consequence, is that this will have a well-defined UV limit. And if we do the UV limit, so we just follow this flow to mu equal infinity, to the high energy, what we find is that it sends epsilon 1 plus epsilon 2 to 1, which is consistent because we see that it sends then this parameter xi to 0. So we get that the right-hand side of the RG flow is 0, so we have 0 beta function, which is what we expect because in the UV we want a conformal model where the couplings do not run. And in the following, I will actually parameterize this UV limit in the following way in terms of KUV and nu. So nu is just a parameterization of epsilons such that in the end the sum is equal to 1. And then KUV is just K rescaled in a specific way. And once again, this is to make some of the expressions later simpler. The details are not so important. Now, this was maybe a little bit abstract. So to give an example, a concrete example, we can look at maybe one of the simplest case of the Klemschik model, which is when the group is equal to SU2. And in this case, it turns out that it's actually equivalent to another model that was found by Fatih, and I think the relation was proven in this paper, which is a certain squashed free sphere, squashed in 2 different ways. And to describe it explicitly, we can introduce some coordinate fields, 3 of them, because SU2 is 3-dimensional. And here I'll do this by using a modified Euler parametrization. So I take my group-valued field G, and I write it in terms of 3 fields, phi, alpha, and chi, in the following way. So once again, the details are not so important, but the 2 angles here, I actually do a specific linear combination. And then the angle in the middle, I take it to be an arctangent of exponential phi. Well, then I put this back into my action. I compute everything. I take the UV limit. And in the end, we find something which is quite simple, which takes the following form here. So we see that, for instance, the boson chi here, it actually, in the UV decouple, it completely decouples. And it just becomes a free boson on its own. And then the 2 other fields, phi and alpha, they stay interacting, but they take a rather simple form here, which some of you might recognize as the cigar sigma model, which is a certain specific 2D sigma model in terms of these 2 fields. And in particular, the cigar sigma model is well known to be a conformal model, which is here consistent because in the end we want a conformal. I mean, the theory should be conformal because we took the UV limit, and here it's conformal because it's the cigar plus just a free boson. And I must say, I mean, this is actually only locally. There are some globality issues, but I won't talk about this today. Now, what I mainly would like to talk about is what happened to the integrable structure when we take this UV limit. So we had all this construction of charges that commutes before the UV limit, and I'd like to see what happens, and in particular what happens to the Lax connection when we take the conformal limit. And so if we do the computation of the Lax connection before the limit, we find that it has actually a very simple dependence in a spectral parameter. So the L plus component depends only on Z, and the L minus only in 1 over Z. And then we see that the part that contains the spectral parameter dependence always come proportional here of the deformation parameter. And then here B and I, they're just some specific currents which are built from the field G, whose expression I don't really need. What's important is the presence of the xi here, because recall that in the UV limit, psi is sent to 0. So if I take the limit too naively, I completely get rid of the spectral parameter dependence, meaning that my lax connection becomes somehow trivial. I can't extract an infinite number of charges from there. So I will need to take the limit in a slightly more subtle way. And for that, I will change my spectral parameter. I will introduce a new one called ZL, and I will explain why L later, which is just xime times Z, and this I now keep fixed. And if I do that, I see that in the L plus component, well, I have xime times Z, so I keep a non-trivial parameter dependence in ZL. But then in L minus, then this becomes xi squared, and then I just have the UV limit of my constant term only. Now I can do something slightly symmetric, which is I consider what I'll call ZR, which is now xi over Z. And in this case, I keep the non-trivial dependence in the minus component, and in the plus component, I get rid of ZR. Now to understand the consequence of this limit, let me focus first on this case ZL, and I'll come back to this one a bit later. So the main property of this limit is that the minus component becomes independent of the spectral parameter. And this means that I can eliminate it very simply by a gauge transformation. So recall that I had this gauge symmetry that acts on the lax connection just by conjugacy of the connection. So in particular, if I take the parameter to be the path-ordered exponential of this B minus, then I can get rid of this particular dependence in L minus, which means that in the end, I should have a lax connection, which in a specific choice of gauge, look as follows. The minus component is actually 0, and then I kept a non-trivial dependence on the spectral parameter in a plus component. And this has an important consequence when I look at the zero curvature equation. So recall that L plus and L minus originally satisfy a zero curvature equation, and this is kept in all of my procedure here, because if I change the spectral parameter, take the UV limit, or change the gauge, I keep the zero curvature equation. And if I look at the zero curvature equation in this gauge, well, because L minus is 0, this simply becomes D minus L plus equals 0. So that tells me that L plus then is a chiral field. More precisely, it's a left-moving field, right? It depends only on T plus X, so it's moved only to the left. And this actually is something that is maybe natural to see appearing in a CFT, because we know that in a CFT we have decoupling of the left-moving and right-moving chiralities. And what we see is this actually happens also at the level of the lax connection, where our lax connection now becomes dependent only on, let's say here, left-moving fields. And let me observe that in general, so these fields BL and IL, which are then the left-moving objects, in general there will be non-local fields, and the reason is that we had to do this gauge transformation by a path-ordered exponent at some point, which then introduced some non-locality in the procedure. So in general, this can be rather complicated field, but they're left-moving, which is nice. Now, of course, I could do the other thing with now the ZR spectral parameter, in which case I get in the end to L plus equals 0, and I keep the minus component, which of course will be then expressed in terms of right-moving field. And this is why I have these notations L and R, therefore left-moving and right-moving. And so to summarize, what we see is that at the UV limit, our integrable structure that initially was defined in terms of just one unique lax matrix, it will actually decouple. It's split into two decoupled integrable structure, one in terms of left-moving chiral half and one in terms of the right-moving chiral half. And this is, well, indeed something that really is quite relevant in the context of a CFT, of a 2D CFT. Now, so all this was maybe once again a bit abstract, so let me give an example of this whole procedure in the simplest case of G equal SU2. So recall that in this case we had just a free boson chi plus a cigar sigma model. And if we do this whole thing of computing the limit of the connection, going to the gauge where it's chiral, we find the following result in the end. So in the diagonal I have some, so these are the parameters, this is the spectral parameter, and in terms of the field, I guess I get D plus chi. And because chi is a free field, then of course D plus chi is left moving consistently as with what we expect. Now what's less trivial is what's happened in the off diagonal, which is related to the cigar sigma model, which is in particular a non-trivial interacting theory. And what we find in the end in the lax connection is the so-called parafermionic fields of the cigar, which are defined as follows. So they're a bit complicated. For instance, they involve some square root of the field, and also the non-local, because there is this dual field here that appear, which is defined as a certain integral. And this in the end comes from this gauge transformation. And well, the details do not really matter. The main property of this is that if you derive the equation of motion of this cigar sigma model, you can check that these are really left moving. They're killed by D minus. And so in the end, these are the fields that I get in my lax connection for this specific case. now in particular, recall that in all that I've studied, I want to look at Hamiltonian property, in particular Poisson bracket of everything. And well, here one can wonder also what happens to the Poisson bracket of the theory in this conformal limit. And in particular, there is a nice property that, so we saw this decomposition in left moving and right moving, and there is a nice property that the Poisson bracket of a left moving with a left moving field will also be a left moving field. So they close in the Poisson bracket, and they form what we call the chiral Poisson algebra. So here we can look at what it looks like for this specific example. So the free boson we know is left moving part plus right moving part. And it's standard that the left moving part then satisfy the following Poisson bracket, where epsilon is the sign function, so -1 and then +1. And in particular, this is a non-local bracket. It's not given only by Dirac distribution. There is this non-locality in the epsilon. If I look at my parafermions, they're actually quite complicating object, but it turns out that they satisfy a quite simple Poisson bracket, which is closed, and which take the following form here, which is then on the right-hand side quadratic in my parafermion, also with some non-local epsilon term, and there's a delta prime that is staying here as well. And this is just a consequence of this definition. And of course, I have similar Poisson brackets for the right, and for the right-moving fields, it's just more or less the same with some signs that change here and there. And then the left-moving and the right-moving, they all commute one with another. And this defines then my two chiral Poisson algebra of left moving and right moving, in which then I can work to guide integrability. So far I had these parafermions, which were rather complicated non-local fields. And I can wonder maybe, are there also some local chiral fields? And in fact, you can find some by looking at very specific combinations of the parafermions. So the parafermions are non-local because there is this dual field here. So in particular, if I take, for instance, psi plus times psi minus, I cancel the exponential, and I get a local object, which is actually quite simple written in terms of the field. And we can check that this is indeed a chiral object. It's a left-moving object. And then I can construct other ones also by looking at derivatives of the parafermions. And for instance, this specific combination turns out to be local. And I can actually build it for every spin. So here this was spin 2, spin 3, and then at spin 4, spin 5, and so on, I will find a new field a new independent field each time. And all of these then form a bunch of left-moving local fields, which actually also are closed in the Poisson bracket. So they also form a subalgebra of my non-local chiral algebra of parafermions, which is what we call the W algebra of the model. So the algebra algebra of extended conformal symmetry, which contains all these local left-moving fields. A typical example of an element in this W algebra, which is always there in a 2D CFT, is the spin plus 2 component of the energy momentum tensor. So the energy momentum tensor of a 2D CFT will have a left-moving spin plus 2 part and a right-moving spin minus 2 part. And in the present case, the spin 2 part, it looks as follow here. In particular, it satisfies also a closed Poisson algebra in itself, which is nothing but the classical Virasoro algebra. And then I can have other type of W currents, also of higher spins, and they all form closed Poisson bracket, which are quite more complicated in general than that, but which are always local in the sense that there's no epsilon. It's only some delta and derivatives of delta. And now a remark is that if I take any field W in my W algebra, because it's chiral, of course, its integral defines a conserved charge almost trivially. So I get a lot of conserved charges, but now because I'm interested in integrability, I would like to ask about involution of these charges. And I find that in general, all of these, they do not Poisson commute one with another. But I can actually find inside of there a subset that commutes by looking at the local charges I had in the Klimschik model initially from the affine Godin model construction and taking the limit. And these turns out to be actually quite simple. The density is simply powers of the energy momentum tensor in the present case. And this you can check from the Virasoro algebra that they all Poisson commute one with another. And so this is quite simple, but let me say that actually this is only a classical result. When we quantize these local charges, they turn out to not be expressed only in terms of the energy momentum tensor. You also need to add other higher spin fields, non-trivial higher spin fields of W algebra. And finally, let me observe that, of course, all this was for left moving, but there is a similar construction for right moving where there is a W algebra, and I can find some charges in involution in there. So to summarize what I have so far, well, the main idea is that we look at the integrable structure of the Klimschik model at the CFT point. And what we found is that classically, we get a lot of non-local and local conserved charges in involution, which quite importantly are now built either in the left-moving or in the right-moving Carroll-Poisson algebra. And the conservation is actually somehow trivial. It's always just a consequence of the chirality. And well, once I have identified my Carroll fields, then of course I kind of trivialize the dynamic. So the conservation property here is not so difficult. But what's important is that it's the involution of the charges, which is, okay, thanks, which is non-trivial. And which is then just, here it's a non-trivial question. I have a certain Carroll algebra with certain Poisson brackets. And inside of there, I want to build charges that commute. So now what I would like to say is just comment on what happened from the point of view of affine Godin model in this limit. So recall that the initial Klimschik model was a relativistic affine Godin model with 4 punctures. And now when I take the UV limit, what I've learned before is I need to take this with different spectral parameters associated to left and right moving. And what happens if I do this is I see that I will have some collision of some of the poles and the zeros of my twist function. And the poles, remember, are the punctures, which mean that in the limits, I get basically less punctures in the end. And so I get 2 different twist functions, phi L and phi R, which have each 3 punctures. And so the interpretation is that this thing of the separation of the 2 chirality happen also at the level of the AGM. Initially, I have one affine Godin model with 4 punctures that describe the whole model. But in the UV limit, I need 2 different affine Godin model, but which have less punctures, so which are associated to less degrees of freedom. And one will describe left-moving, and the other will describe right-moving fields. And that leads us in particular to the definition of what we'll call a left-moving, a Carrollization. So here left-moving, but they could be right-moving. So it's still a realization in the sense that my Kac-Moody current are expressed in terms of canonical fields in T star Q. But now we ask in addition that the dynamic is such that the theory decouples into 2 Carroll halves of left and right moving. And we ask that our Kac-Moody current JR, they're here expressed only in terms of, let's say, left moving fields. So they're in a left Carroll-Poisson algebra.
Maybe I missed this point. So in SU2 cases, you mentioned in the conformal limit, you just get SL2R coset model times the line.
Yes.
Can one make some more general case comment about what is interpretation of other general case?
So for instance, for higher rank group, we don't have a proof. But what we kind of expect, looking at some cases, is that it will become just rank G free boson plus the CFT point of the coset G over H, where H is the Cartan subgroup. And this, at least in terms of the, I mean, we computed some Poisson algebra of like parafermionic-like Poisson algebra and the gauge fixing of this higher rank model, and we find something which is consistent with having basically the parafermion of G over H and then rank G free boson. Okay. So here in this definition, so in this left-moving Carrollization, so the Kac-Moody current should all be left-moving. And actually, to be more precise, they should be left-moving in a specific gauge. And so this is because, remember that to get to really the case where the Lax connection in the end is left-moving, we needed to do a gauge transformation. So here, the Kac-Moody current in a specific gauge fixing, they should be left-moving. And then all the things that I presented before, they can be reinterpreted in terms of affine Godin model. So in particular, these gauge fixed currents where they become left-moving, they will become my non-local Carroll field. So this is how I will get, for instance, the parafermions from the affine Godin model. And then the local Carroll fields, so the W algebra, they correspond to gauge invariant differential polynomials in my Kac-Moody current, and they form what is called a coset W algebra in the standard terminology. So now what I want to do just in the few minutes that I have left is just to say a few words about the quantization of this. And so the idea is that now that we have this integrable structure in Carroll-Poisson algebra, we have a rigorous and well-controlled setup to go to the quantum level because we know how we quantize Carroll-Poisson algebra. These quantize in what are called vertex operator algebras, which then describe the quantum Carroll fields and their commutation relation. And now with this picture, I now have a well-defined framework to ask about the construction and diagonalization of commuting charges in these VOAs, which can be either local or non-local in the quantum Carroll fields. And this is then a hard but well-defined mathematical question, which is really what here, for instance, the CFT brings us. And for instance, if I look at AGM, if I look at quantized AGM, this will be described by a certain, what we call the affine Kac-Moody VOA, or actually n copies of this affine Kac-Moody VOA, which describe my quantum Kac-Moody current JRX. And the Poisson bracket that I had for the classical currents. Now, at the quantum level, they become commutation relation, which are encoded in the language of VOA in operator product expansions. And the OPEs of these Cox-Moody current, it looks as follows. So there's a simple order pole here, which is the delta term in the Poisson bracket. And there's the second order pole, which is the central extension, so the delta prime term, proportional to the now quantum level KR. In particular, now that I have this OPE, which encode my quantum commutation relation, I can ask about the integrable structure. I can ask about building some specific combination of these quantum JRX, either local or non-local, which would be then commuting. And then also I would like to find the spectrum and diagonalize them on some representation. So here it's not fully understood yet, but there's a lot of first results and conjectures that shows that this integrable structure at the quantum level should exist. And in particular, we can look at what happened for this specific case of the SU2 Klimschik model in the UV that I had. And here there's two main approach. Either I look at things coming from affine Godin model point of view. In particular, I have a rather simple description of the quantum coset W algebra as a certain specific coset. And inside of there, I can ask about the quantization of the local charges. So these quadratic and so on charges, we can quantize at least the first ones using some results here. And then another approach is based on what are called screening charges in free field realization. So I won't have time to explain about this, but just to say that in the end, this gives us some conjectures and results about also the quantization of the local and non-local charges in this model. And what we checked in our paper is we look at the agreement of the first local charges. So the first local charge is the spin 2 density. This is actually rather simple to quantize. It just becomes the quantum energy momentum tensor, the density. But then the first non-trivial one is a quartic one, so a spin 4 density. And here we computed it from the affine Godin model point of view and from the screening charges, and we find that it exactly then coincide, which is already a non-trivial result in this case. So this then was mostly what I wanted to say. Let me just briefly conclude. So what I presented about this first step then towards quantization of integrable sigma model using AGMs at the CFT point. One of the interests of AGM is that it brings a lot of hope for natural generalization and perspective. So for instance, going higher rank for the Klimschik model, and here, well, we have some first initial results in the paper, that there are still a lot to explore. And mostly is the idea that we can apply these to a quite larger class of relativistic AGM. So recall that the Klimschik model corresponded to 4 punctures. So I can look at more punctures of a type of punctures, for instance, of higher order poles and so on. I can change the realization and, for instance, go to lambda model rather than Young-Baxter deformation. And all of these ideas, looking at the CFT limit, should also apply to all this zoo of fear. And then also we can ask about what how all this can be interpreted in other formalism, like the E-models or the Fordich and Simons formalism, which we know are related also to the AGM construction. Then, so far I focused only on constructing the quantum charges that commutes, but then we can ask about diagonalizing them and describing the spectrum. And here let me say that there is a very powerful approach which is called the ODE IQFT correspondence, and which was actually one of the main motivation behind the introduction and the study of affine Godin model and also of our paper. And well, I won't have time to describe, but here we also made some check that there is some agreement of what come from affine Godin model and what come from other approaches in this paper here. And finally, let me say that probably the most important but the most difficult question is to go beyond the CFT, so to try to go to points which are not fixed under the RG. And here this is of course quite a complicated question, but maybe one can hope that the CFT can serve as an entry point, and we can start with the CFT point and then try to build from there the massive case by putting back together the left and right moving chiral halves, and hopefully at some point get some result about the integrable quantum structure from first principle. And with that, I end, and thank you for your attention.
Questions?
I think that was
Yes, if we add the West-Suminovitan term, like yesterday Fiona did, this is still covered by this affine Godin model?
Yeah, so at least we didn't really look at the conformal limit, but I think so. It's some unpublished result, but this case is also an affine Godin model. The only difference is it changes a bit the levels.
But it remains 4 rank.
Yeah, it's
four punctures.
Yes, exactly. It's still 4 punctures, but then it changes a little bit the levels that enters in the affine Godin model. In particular, one of the effects is here, because there was no Vesumiano term, there was some kind of parity symmetry between left and right moving. And actually, the left and right moving affine Godin model, they had the same level up to a minus sign. And this actually will be broken if we add the Vesumiano term. Actually, the Vesumiano level we just add to this level directly, and then the left and right moving will be slightly different algebraic objects, basically. But it should be covered, I think, from this construction. Yeah, done.
I mean, the ones yesterday were multi-parameter conformal deformations. Right? There was a marginal manifold of theory. So if you start with like a super coset version of this, do you hit the VOA on the head from the outset?
That maybe not. I mean, one of the things here, we really had to take this very specific limit in which it becomes conformal. I guess if you have a supergroup, and if you start with a supergroup which have like vanishing Coxeton number, then you will always have then conformal invariance. But I'm not so sure how easily it is then to identify the left and right moving sectors and whether we can do a whole this construction as simply as that. So that for the super case, I think in some sense the origin from conformal invariance is maybe a bit different. It's I mean, of course there should be some relation, but it's really because in the end there is this H check that cancel, which is slightly different mechanism than what happens here.
So this is a bit related to Akari's question earlier, but so you started from SU2 and then you end up with SL2R over U1, and I guess the question is, so do you need to glue together formally different cigars to?
Yeah, so this is part of what I meant when I said that here in the limit there was this locally. So there's two things actually behind this, which are to do about the target, how the target space looks like in the limit. So first of all, actually this thing of free boson plus cigar, it's not exactly true, because the free boson chi, it's not really on a cycle, because if I look at the basically the identification, when chi goes to chi plus 2 pi, I actually need to change also the value of alpha, so I kind of glue it non-trivially on there. So here there's also, it's not completely separated, the cigar and the field. And then also there is this thing that there is all the charts. So it's a bit like the sausage that in the end on one chart will become the cigar, on the other side will become the right cigar, and in the middle there will be some asymptotic domain, which is just the cylinder. Here there will be something quite similar. There is, on one, I can get the left cigar here. I can get another cigar with another way of taking the limit. And then in the middle, I have basically some free field, which is where I get these screening charges and the free field realization. And actually these two, what's also important is that it's not phi and alpha that are the coordinate of the other cigar. It's actually so phi stay the same, but then instead of alpha, I have alpha twiddle, which is a non-trivial mix of alpha and chi. So the gluing is rather non-trivial here, which actually I think is one of the reasons why we can't really say that this is just the cigar integrable CFT plus the free boson. There's some non-trivial thing that actually are kept track here in when we glue things together in a non-trivial way.
Okay, thank you. And just another question. So I guess SU2 is very special in the sense that the model you end up with is real.
Yeah.
Just out of interest, the whole conserved charge stuff, does that go through for when it is?
Yeah, so you ask about the art questions. So indeed here we had to take this analytical continuation to get a non-trivial UV fixed point, and we were safe because in the for the SU2 case, so in general what we would get is we get a real metric but a imaginary B field. And in the case of SU2, the B field turns out to be total derivative, so we can get rid of it. For a higher rank, in general, we should probably keep some non-trivial B field. But in some sense, it's not such a problem for all the algebraic manipulations we do. I mean, maybe there will be some issues with, for instance, unitarity of the CFT that we're going to consider. But if we just ask about commutation relation and building stuff that commute, that should probably go through. Another point on that is maybe also we can look at case with non-compact group initially, and in this case we should have we can take the split R matrix directly, and then it should work. But then we lose the boundedness below of the Hamiltonian probably.
Thanks for the nice talk. So the first question is really about the Maya bracket. So when you take this limit and you go to the UV, so there are some models like the K-deform PCM where you take a limit and you completely ultra-localize the model. But here when you take the limit, it seems that the twist function is not a constant. But could there be like some gauge transformation where the Maya bracket ends up being ultra-local?
No. So there is an example. So it turns out that, for instance, the cigar, if you take the sausage grid to the cigar on its own, then here there's a gauge where it will become non-ultra-local, ultra-local. But actually, in the case that we're looking at here for this full Klimschik model, there's no gauge where it's ultra-local, except if you put the parameter nu to 0, which effectively goes back to the cigar, actually.
I see.
So here we really can't get rid of non-ultra-locality.
I see. And one more question is, you have W algebras appearing in your setup and also affine catch-Moody algebras. So you can get W algebras from affine catch-Moody algebras from generalized Siegel-Sugawara constructions. So are these related in that sense, or are these like completely different
Yeah,
objects?
so I mean, here it turns out that, for instance, the W algebra that naturally comes from a affine Godin model is built as a coset W algebra. So I take just 2 copies of the Kac-Moody current and I quotient by the gauge symmetry, basically, which is, and then, for instance, the 2D, the energy momentum tensor in there is built by the Segal-Sugawara there, the Segal-Sugawara there, minus the diagonal Segal-Sugawara, which are this kind of JKO construction, for instance.
Thank you.
Yeah, Tom. So 2 questions. The factorization that happens, do you expect that to just be in the CFT limit? Do you expect that to be generic?
Yes, so this, at least at the classical level, we looked at this very general class of relativistic AGM with more punctures, arbitrary punctures, and so on. And we have some kind of general argument that there should be a limit in which we have this property that we have 2 lax connection, and one will have 0 minus component and the other 0 plus component. So there should always be Carroll fields that we should extract from there.
Okay. Have you any idea about how you might specify the affine Godin model data in terms of the CFT data? Like we can factorize CFTs, right? We understand really well how to do that. So maybe you can see what the CFT data is in terms of the affine Godin model.
Yes, so I think partly. So, for instance, the central charges can be very easily obtained because, for instance, we have the W algebra as a coset construction, so we can apply the general formula for the central charge. Another thing is, well, if we ask about what is the quantum VOA, then actually it should always be something built as, well, having a bunch of Kac-Moody current and building and then gauging this. So for the local charge, we, I think, understand that pretty well, and it gives us the for the local densities, it gives us the W algebra. Then, for instance, there should be a way to take quantum Kac-Moody current, do some BRST reduction, and we get, for instance, the parafermions and all that. So in general, we should have access to the algebra, even of non-local Carroll observables from there, although in practice it can probably be quite difficult.
Okay. And do you have any idea about what happens to this factorization as you move away from the CFT limit?
So probably then it will be broken, right?
Yeah. I mean, but it might be like if it's still integrable, you'd expect it to be that you at least you'd hope that there might still be some nice structure going on. So
probably what should happen is we should recombine the left and right moving halves in a very specific way. That is, we do a marginally relevant perturbation from this point. That it will be probably like quadratic in left and right moving stuff, chosen in a very specific way that ensures the integrability of the theory. But doing that at the quantum level, I think, for the moment is quite hard, right?
I think we're running short on time, so maybe let's thank Sylvain again.
I'm happy to discuss anything later.
So let's start. So it's a pleasure to introduce the next speaker. So Jeremy Mann, who will be telling us, so coming from DESI, and who will be telling us about conformal blocks in D dimensions from Godin models and applications. Thanks.
Yes, so thank you to all the organizers for putting together a very stimulating conference, and thank you for the opportunity to present my work based on papers with Sylvain, who just gave this great talk, Ilya Buric, who talked about similar things at IGST, Lorenzo Quintavalle, and my supervisor, Fogo Chomerus, and towards the end I'll also discuss some work in preparation, should come on the archive this month with Apratim Kaviraj. So the general idea is to compute a basis of functions using quantum mechanical integrability. And I want to give some motivation and explain the context for these bases of functions. Consider a semi-simple Lie algebra G and unitary irreducible representations. In a physical context, these will be like one-particle Hilbert spaces. And mathematically, we realize them as quantized coadjoint orbits, such that the generators of G act like first-order differential operators. And we're interested in the space of G invariants in the tensor product of these representations, which we call endpoint functions. Because in conformal field theory, these will be the correlation functions of n primaries, and the G invariants correspond to the conformal ward identities. So we know from group theory, or just solving the G invariance conditions, that the two-point function is fixed up to a constant and is normalized with the scalar product. And three-point functions correspond to Clebsch-Gordon coefficients. So we can always decompose this n-point space into three-point spaces just by taking sequences of decompositions of these tensor products of one-particle Hilbert spaces into direct sums of irreducible representations. And we can represent this sequence of direct sum decompositions in terms of what we call channels. And they can be written diagrammatically with what we call OPE diagrams, which are just these binary trees where the vertices denote the three-point functions, the spaces of three-point functions in this decomposition. So this is a general procedure. Of course, just with group theory methods, this is quite complicated to do. And so our goal is given any such channel labeled by an OPE diagram to construct the basis of G invariant functions, which we call endpoint blocks, which will be labeled by the Dynkin labels or quantum numbers of the representation in the tensor product decomposition, and the Clebsch-Gordon coefficients of the three-point functions in the decomposition, which are attached to these three-point vertices. So I'll always be using this diagrammatic notation for a function which will depend on all of these coordinates x's on my coadjoint orbits, which in a CFT context you can think of as points in Minkowski space. So our main focus, our main motivation is to apply this to the analysis of conformal correlators and to constrain their coefficients using bootstrap methods. But I want to emphasize that this is a very general problem with applications in scattering amplitudes and in mathematics to various constructions in geometric invariant theory and quiver representations. So this is the problem, and our approach is using integrability. So we extract from the Godin model on the n-punctured sphere a complete set of commuting operators. This defines a quantum mechanical integrable system, a many-body integrable system, such that these blocks are simply eigenfunctions, eigenvectors of this complete set of commuting Hamiltonians. So,
excuse me, how do you know that it's complete, this set?
I'll get back to it. We can apply a sort of recursive construction based on the fact that we have procedures to do to apply a quantum Hamiltonian reduction to three-point subsystems, and then we assume completeness of the three-point Godin model. There's no limit. When n is equal to 3, there's no limits to be taken. So we literally have a three-point Godin model, and we're using results of the literature that this is complete. So it goes by this recursive construction, or this constructive approach, which is very much important in our approach to solving and studying these systems. So the idea is that for any number of representations in any channel, we have a quantum mechanical integrable system. And we can generally relate these systems, these blocks, at higher number of points and lower depth, meaning lower number of Dynkin labels in quantum numbers, to systems with lower number of points and higher depth. And usually, we know less about these higher end systems, but we're more interested in computing them. And we know more about these lower end systems. So our approach is to use various techniques like what we call OPE limits and shadow integrals in the CFT literature to relate higher n to lower n higher spin. And so in particular, we can construct these higher n blocks as integrals of products of these 3-point blocks. And we can take limits of higher n blocks to lower n blocks. And so to be a bit more specific, for n equals 3, 4, we've made various identifications.
Maybe just one more question. You know, somehow it seems to me that in conformal field theory, not all invariants play the role of correlation function. There are some fusion rules which exclude some of them. And so would you comment on that?
So I should have specified that we're almost always considering, so we're considering global conformal symmetry.
Just global.
Yes, so this does not really apply to, yes, exactly. So SO2 comma D is one application.
So just to be sure, so this is the Godin model associated with which Lie algebra then?
It can, so in conformal field theory, it will be SO2 comma D. Unitary representation of SO2 comma D. But this is a construction that applies to any semi-simple Lie algebra. But indeed, keep in mind SO2 comma D for CFT applications. Right, so for n equals 3 and 4, we've identified these integrable systems with known models of Keller-Sutherland and Keller-Moser type associated to root systems like BC2 and complex reflection groups like Z4. And so I'll put these integrable models under the umbrella of CMS systems. And for n larger than 4, we can be able to use these results to get various integral representations of our higher point blocks and to get solutions in limits. And we understand them enough for some first applications to the bootstrap, which I'll sketch towards the end of the talk. So my plan is I'll give a talk in 3 parts. First, I'll review the construction of the n-point blocks integrable system from Godin. Then I'll discuss the limits and interrelations amongst these integrable systems at higher n, lower depth, lower n, higher depth, and the derivation of these CMS type models. And I'll finish with explaining some first applications to the analytic conformal bootstrap, so analytic ways of solving these crossing equations near singular points. So let me quickly review our starting point, the Godin model on the n-punctured sphere. So we put each of these n irreps at a puncture. We use the lax matrix of Godin with a group Lie algebra index alpha, and we attach to each puncture the action of the conformal algebra on this representation. And there's a standard construction that gives us invariance by contracting the symmetric tensors of the Lie algebra with of degree p with p copies of the lax matrix. If we add the appropriate quantum corrections known in the literature, we'll get that all of these invariants commute amongst themselves. And we can see manifestly that this object is a global G invariant, so it should commute with the diagonal action of the Lie algebra. So we have 2 ways to construct our integrable systems. One is bottom up. The idea is we take our OPE diagram, our channel. We consider any vertex in it. It divides the set of points into 3 subsets. And we can consider the diagonal action of the conformal algebra on this subset. So in other words, the sum over generators at each of these points. And we define a vertex lax matrix, which looks exactly like the lax matrix of a 3-point Godin model. And to eliminate the dependence on punctures, we set them to 0, 1, and infinity. So we apply exactly the same construction I gave before. We construct these invariants of this vertex lax matrix. I'll use the shorthand notation L to the P for the contraction with the invariant tensor. And once again, the appropriate quantum corrections. And playing around with the global G invariants, we can show that these two invariants at different vertices commute. And using properties of the 3-point Godin model, we can show that the invariants at the same vertex, different degrees, also commute. So we have a set of commuting operators. And to give you an intuition behind why we expect this to be complete, we can essentially take the highest order pole in each of these invariants and get Casimir operators associated to these internal legs. If we diagonalize them, so employ a Hamiltonian reduction, we get Casimirs associated, which give us the quantum numbers of the representations propagating in these tensor product decompositions. And if we look back at our vertex invariants, these will just reduce to invariants of 3-point Godin models, which will describe our 3-point blocks. So this is the bottom-up construction. We can also use a top-down construction and obtain these vertex lax matrices as limits, so scaling limits of the n-point Godin lax matrix. Essentially, we appropriately rescale the lax matrix and scaling parameter, and we make the punctures depend on these functions f of the, so these are polynomials in the small variable var pi. We have a general construction in our paper. I'll give a simple but important example, the n-point comb. So the construction of these polynomials that define the scaling limits, they're based on a certain ordering of the vertices. So this is called a rooted tree, or in this case, binary rooted tree representation of the OPE diagram. We make the last puncture go to infinity, the next to last puncture go to 1, and all of the remaining punctures go increasingly fast to 0, depending on how low they are in this ordering of the vertices. And similarly, we make the spectral parameter and lax matrix go increasingly fast to 0, depending on their depth or their position in this ordering of vertices. So if you take the rth vertex here, take this scaling limit, you'll pick up just the generator at the r+1th leg at w minus 1, so at the point 1, and you'll pick up all of these 1 to r generators at the pole 0. So in this way, we recover the vertex lax matrix of the comb channel integrable system from these limits. In fact, this kind of limit was already studied in the literature under the name of bending flows or caterpillar limits. But our construction generalizes to any possible channel, so any of these imaginable binary rooted trees. So we've constructed in this way a complete set of commuting Hamiltonians. In practice, so far we've only expressed them in terms of products of Lie algebra generators acting on single points. To manipulate them explicitly, we realize them as differential operators on this space of n-point functions. So as a representative example, the most important in our eyes, we take the conformal group. For applications, we usually consider n scalar primary fields, where the fields dilate with scaling dimension delta, and they transform like a scalar under the Lorentz subgroup. And we can solve the what identities explicitly by writing our correlator of n points as a homogeneous prefactor of the distances squared times a function of the cross ratios. And some basic group theory counting gives you the cross ratios in the number of cross ratios in arbitrary dimension. I apologize for the typo here. So in fact, the counting goes as follows. If n is sufficiently small, smaller than d plus 2, then the conformal group acts transitively. So I just subtract the number of degrees of freedom by the dimension. And for sufficiently large number of points, the conformal group no longer acts transitively. I get a stabilizer, and the number of cross ratios just becomes n times n minus 3 over 2. The only thing that's important or interesting to know is that the critical dimension, so d equals n minus 2, at which the number of cross ratios stabilizes. So we have this representation of endpoint functions. We can act on this correlator with our generators, and we realize our commuting Hamiltonians as differential equations in the cross ratios. Maybe a last thing I can specify is that we can generalize this construction to more general representations, spinning representations of SO2 comma D, or general representations of other Lie algebras, and we obtain the same kind of differential operators. So to summarize, I've explained how to obtain a complete set of commuting Hamiltonians that determine endpoint blocks in any channel, starting from the Lax matrix of the Godin model. If there are no questions, I'll move on to part 2. So part 2, I want to relate subsystems at different numbers of points and different depths via various relatively basic CFT techniques. So the intuition is quite simple. This shadow integral that I call, so these integral representations, they come from intuitively taking the resolution of the identity in your correlator, which projects your tensor products into one particle Hilbert spaces. And these OPE limits, they come from the behavior of these correlators in OPE limits comes from the cluster decomposition principle. So if I separate my points into two distinct clusters, and my distances, so my length scales are such that the distance between the two clusters is much larger than the distance of points within the two clusters, then I expect a factorization of my correlator. And if I'm a bit more specific, these two clusters, so these two correlators, should only interact via an operator O of lowest scaling dimension and spin. So these are our sort of physical expectations, and these statements should have an incarnation in blocks and into these endpoint block integrable systems. And this is what we've done. So these shadow integrals, which were first done by Ferrara et al. In the 72, we can do them for more general endpoint blocks. And we indeed get a certain integral over position space of a product of correlators, which I won't go into detail. It's just a way to say that if we know 3-point block integrable systems, we can use them to express my higher point integrable systems in this way. So then moving on to the OPE limit, this cluster decomposition, we've been able to find a good set of cross ratios associated to the legs and vertices of our OPE diagram, such that this kinematic limit I described, where we separate two clusters, corresponds to the limit where these cross ratios go to 0. And in this limit, we found a factorization of blocks into two lower point blocks, in this case, two spinning 4-point blocks, and certain power laws. So we've derived this result from integrability in the sense that we found this power law behavior and the correct exponents in terms of the quantum numbers by diagonalizing the Casimir operator at the middle leg. And we have proven this factorization into 4-point functions by taking the vertex invariance of the 6-point function, imposing this power law ansatz, acting on it, and obtaining that these 6-point invariants reduce to 4 points invariance on either side. So this is how we implement the OP limit, and now I want to show how we obtain the integrable subsystems of lower points we obtain in this limit. So as I said, we take this OP limit at the middle leg, we get two 4-point functions. I act with the second order Casimir for my left leg here, and I obtain a spinning hyperbolic BC2 Keliger-Sutherland Hamiltonian. It's a second order operator in 3 variables, the 3 variables of this 4-point function, and it depends on 3 parameters. Quantum. This is all quantum. So these are wave functions. I'm sorry if I'm not making this very explicit, but these are all wave functions, yes. And so these are differential operators, and this is also a differential operator. So I can go further. I can take one of these 4-point functions, take another OPE limit to a spinning 3-point function. I can act with this 4th order differential operator that I obtain from my vertex invariance. And I obtain the Hamiltonian of an elliptic Z4 Keliger-Moser Hamiltonian. So it's a 1 variable differential operator, 4th order, 3 singular points, and 6 parameters. Let me say that this has not yet really appeared in theoretical physics, which is perhaps unsurprising because it's a Hamiltonian of 4th order. However, in the mathematical literature, if you dive in deep enough, you can expect such results, though it has never been derived explicitly. Essentially, we have this, using constructions from quiver representation theory, we can expect this more general pattern that you can associate to each star-shaped affine Dynkin diagram a 3 or 4-point Godin model, but this time for G of type A. The construction is rather intuitive. So for each of the legs of your Dynkin diagram, you associate a representation whose depth is the same as the number of nodes. The group is SLN, where n is the maximal number of nodes on a leg, and we obtain various Keliger-Moser integrable models in this way. I should caveat that, so this is an expectation. We haven't derived it explicitly, but based on results from quiver representation theory, we expect it to be the case. So where I was getting at is you could have expected this kind of result for 3-point Godin models based on a quiver theory for G of type A. But it's still rather surprising that we get this 1-parameter infinite family of CM models for G of type BD, where it's the same CM model, but just with shifted parameters depending on the dimension. And this points to a more general trend that for sufficiently large, so essentially when the number of cross ratios stabilizes, we get a smooth dependence of our integral models on the dimension. And this is really a completely novel result where very, very little has been studied on these kinds of models for G of type not of type A, and even mathematicians would have been surprised by this kind of result. Okay, so moving on to summarize, I've explained how to get subsystems, how to relate integrable systems at lower n higher depth to higher n lower depth. And I've explained how we derive that these integral systems at n equals 3, 4 are of CMS type. So if there are no questions, I'll finally move on to applications to the analytic bootstrap. So for our intensive purposes, we can just get, we can understand the approach or the philosophy of the conformal bootstrap very simply. We take the given correlator, an endpoint correlator, expand it in 2 different channels, and the goal is to constrain or get information on the quantum numbers of the representations propagating in each channel and the coefficients of this decomposition, which have a physical significance. In the bootstrap, to make this really constraining, we posit the existence of an associative operator product This gives us an interpretation of the coefficients in the n-point function as products of coefficients in 3-point functions. And finally, unitarity, which constrains the conformal dimensions and spins of the representations that we're allowed to sum over. So in particular, the scaling dimension is bounded by the spin. So this is, of course, a very difficult equation to solve, to study, to get constraints with. Generally, we have two approaches. One is to study this equation near a regular point and to get approximate, or to get numerical solutions. An important tool there is to use the fact that these products of OPE coefficients are positive. But I'll be discussing really the other approach, the analytic approach, where we study both sides of this equation near the same singular point. And the hope is that if the behavior near the singular point simplifies these blocks, this integrable system enough, then we can really get constraints on these coefficients. So let me start with the most basic example, 4 identical scalars in d equals 1. So it corresponds to taking the SL2 Godin model on the 4-punctured sphere, taking 2 limits on either sides to get 2 distinct channels. And we write the crossing equation by equating the expansions in either basis. Sorry, there's a typo here. This is a 2 delta phi. So we obtain this the following equation. The associative OPE tells us that these p deltas are the same coefficients. These psi deltas are known to be, so these blocks are known to be wave functions of BC1 Keliger-Sutherland Hamiltonian. They take the form of hypergeometric, Gauss hypergeometric functions, but we don't need to know this for my derivation. And I want to study this equation near z equals 0. So as I said, I have 2 BC1 one particle Hamiltonians. I can put them in Schrodinger form by appropriate change of variables. And the z goes to 0 limit corresponds to different limits in my 2 integral models. So on the left-hand side, I'm taking t goes to infinity. This potential, it goes like 1 over sinh squared t. So it'll vanish when t goes to infinity. I'll just get these plane waves. And these plane wave solutions, they'll suppress higher scaling dimensions. Very similar to, in fact, this is a realization of the OPE limit in this side. On the other hand, I'll be taking t prime goes to I pi if I put in this change of variables. And once again, I'll have a 1 over sinh squared potential in t prime. But this will lead me to a inverse square singularity in the potential. And so I'll be reducing my 1 over sinh squared potential to inverse square potential. This is known as a rational degeneration. And I'll be reducing my BC1 model to a rational A1 model. So these models are much simpler to compute, and we have explicit results for the wave functions in terms of modified Bessel functions. OK, so this is the 2 sides of my, the 2 models I'm looking at. And so to summarize, I have a plane waves on this side where the scaling dimension is suppressed. So at leading order, I just get a constant, which is normalized to 1. And on the right-hand side, I'm summing over eigenfunctions of a rational A1 model. The only way to relate these 2 sides is to make a scaling ansatz, namely that delta is large and it scales like 1 over square root z. And if I posit this scaling of the OPE coefficients with respect to large delta, then I solve the crossing equation. So at the end of the day, what I get is the asymptotics of OPE coefficients at large scaling dimension. Right. So this is when delta prime, so this delta is on scales below this one. So I can verify that if I put in a cutoff L and integrate this function, the corrections will go like L to a power and they'll be suppressed. Sorry, Z to a power and they'll be suppressed. So my point is that it doesn't matter exactly what this cutoff is. As long as it's finite, it's subleading. Yeah. OK, so this was the simplest case, but this is really the main idea. I can solve at leading order if I know how my integrable models behave in these limits. So I can do the same thing for the next simplest case, I guess, is 4 identical scalars in D larger than 1. I get an SO2, D Godin model, 2 channels. It's known, thanks to Isachenkov and Chomeros, that these are BC2 Calogero-Sutherland integrable systems. And the crossing equation takes this form. Once again, these coefficients are the same on either side. And a very constraining limit, the one that's used in CFT, is to consider limits in Minkowski space, so in the Lorentzian regime, where neighboring points are light-like separated. So in these cross ratios, that corresponds to Z equals 0, Z bar equals 1. And I'll proceed by a very similar analysis. So essentially, I'll start by first taking Z going to 0, so x1 and x2 light-like separated. And on the left-hand side, my 2-particle Hamiltonian decouples into 2 1-particle Hamiltonians and a plane wave. Whereas on the right-hand side, I'll get a inverse square divergence in my potential and a rational A1 model. On the left-hand side, my plane wave, its momentum goes like delta minus L, which we call the twist. And so this means that the higher twist will be suppressed. And on the right-hand side, as I said, I'll have to sum over the eigenvalues of this rational A1, which will go like the anti-twist, so delta plus L. If I take the second limit, I'll reduce the second particle to a rational A1. And I'll reduce the second particle on the right-hand side to a plane wave, whose momentum will be also given by the twist. And if I plug this into the crossing equation, I'll have to identify the momentum of this plane wave, which goes like, which enters like 1 minus Z bar. Make sure it cancels with this prefactor here in the crossing equation to reproduce the leading term on the left-hand side. So what I get is a sum over blocks with twist 2 delta phi, which I can interpret as these kinds of composites of the external scalar. So finally, I have to solve so I've solved for the dependence in 1 minus Z bar, and now I have to solve for the dependence of Z, and I obtain a very similar behavior as the one-dimensional case, where I'm relating a plane wave here with a sum over rational A1 models. And at the end of the day, I obtain this very simple equation, which is solved by power law asymptotics in the OPE coefficients at large conformal dimension and twist. Sorry, large conformal dimension and spin, with the twist fixed to be 2 delta phi. OK, so this has been known for a while now, since 2012. But it's always this same idea. And so for what we've been doing is for 5 and 6 identical scalars, doing essentially the same process. We have many more cross ratios, so 5 cross ratios for n equals 5 particles, 9 cross ratios for n equals 6, so the equations are much longer to do. But it's the same idea. We take limits where points are light-like separated, as many as the number of degrees of freedom. We get various decouplings of our Hamiltonians into plane waves and rational degenerations. And we get solvable equations that are solvable analytically, where we relate a plane wave to a superposition of rational wave functions. And at the end of the day, this gives us OPE coefficients at large delta and L, depending on the exact setup, also large, the other quantum numbers being large, with the twist fixed. OK, so I hope I could communicate with you our general approach and the idea that we don't need to know the exact integrable model to solve this crossing equation at leading order. We can just need to know its behavior near the singular points. So to summarize, we obtain this complete set of commuting Hamiltonians. We relate higher n lower depth systems to lower n higher depth, and get explicit solutions in terms of CMS type integrable models at low n. And using our results on limits and integral representations of our higher n models, we can do analytic bootstraps, so we can obtain OPE coefficients of operators at large quantum numbers from rational degenerations of our integrable models. So let me move on to the outlook. So in terms of the endpoint Litecoin bootstrap, what I'm describing really only scratches the surface. And so in the case of 4 scalars, I just explained the leading order solution to the crossing equation in this limit. But people, since 2012, have spent a lot of time and efforts expanding it at higher orders and understanding better what's going on. And thanks to a more detailed knowledge of blocks, we were even able to derive, Caron Huot was able to derive that the large spin expansion, so the expansion at large spin and fixed twist of the CFT data converges down to spin 2. So this is not just an asymptotic expansion, this is a convergent expansion that we can really do systematic analysis with. So for n larger than 4, this is a very important and interesting open problem, and we're hoping that starting from this very basic analysis that people did in 2012 for the 4-point function, that we can get to the same point as them, or at least answer this open question of whether the analytic properties of this large spin and large quantum number expansion. So finally, from the integrability point of view, another point of interest is that essentially these vertex degrees of freedom, so these higher order Godin operators, are very difficult to solve. And what we've been investigating to some extent is the extent to which these vertex degrees of freedom can be dealt with and encoded by a superintegrable structure. And in some simple cases, like n equals 5, we have a lot of evidence for this, where we can essentially replace the eigenvalue problem of this vertex operator with just an algebraic approach, where we just posit that our eigenfunctions are representations of these operators A dagger, which commutes with all of the other Hamiltonians. And so we've been able to construct these in n equals 5 in certain light cone limits, but it's an open question to what extent the superintegrable structure exists at higher points. Finally, it'd be quite interesting to study Q deformations of the models we obtain. So we know that for these CMS models at n equals 3, 4, these admit Q deformations into double affine Hecke algebras, which have been studied for a while now. These are associated to either the root systems or to these affine Dynkin quivers that I showed you. And so for us in CFT, it's actually it can be useful to use these, to have these Q deformations to derive various relations between blocks at different quantum numbers. But also from the integrability perspective, it would be very interesting to understand how this generalizes to higher n, and how these Q deformations lift to Godin, since we know that we get these CMS models from limits of Godin. Okay, so that was all I was going to present. If you have more questions on this last part with, well, if you have any more questions, feel free to ask.
Just I have one terminological question about your last transparencies.
Yeah.
So normally I thought that Calogero model is rational, Calogero-Sutherland is trigonometric or hyperbolic, and elliptic Calogero is elliptic. And now that the Calogero-Sutherland is Q-deformed Calogero model, and now it seems that you use different terminology. So what is for you is CMS model?
Yeah, for me, so we use the terminology that there is rational, trigonometric or hyperbolic, and elliptic Calogero-Sutherland Hamiltonians, depending on whether the potential is rational. So 1 over a power, 1 over...
So for you, CMS is all of that?
Exactly, it's all of that.
Okay.
And in particular, one of the models we got was an elliptic one. And another one
this was an elliptic one. Yeah. And now, this double affine Hecke algebras, it's still many-body integrable system?
Well, no. We only know... I mean, sorry. We only get this for these CMS models, which are at most... in our case, we can only connect it with at most rank 2.
Yeah, but those are integrable many-body systems, CMS. And double affine Hecke algebra is what?
Yes, okay, that's a good point. But yes, double affine Hecke algebra, it's...
Is it a dynamical system in this, on some way, or in some way?
It's... honestly, I can't say for sure. It's an algebraic structure. It's a deformation of a Q deformation of our operators that reduces at Q equals 0 to integrable models.
You can say that there are Q-deform eigenstates of CMS systems or something like that?
Yes, I think that's correct, yes. I mean, essentially, you'll replace your differential operators with Q difference equations. And you can interpret these Q difference equations as Schrodinger problems of a Q-deform system.
Probably.
Just a quick question again about this Q deformation. This has some, or you think it might have some interpretation at the level of the conformal field theory? Some physical meaning? I mean, some...
Yeah, that's a good question. Not that I'm aware of. So far, it's when we have looked at it, it's just been a useful tool to derive what people relations at Q equals 0 between different. But it's an interesting question. I think a similar question is what we effectively get with Godin models is an interpolation between blocks in different channels, and it raises the question: does this also have applications to CFT, to have a deformation of the blocks and a basis of functions to expand correlators with, whose limits give you OP coefficients?
You mean is there some physics to the middle bit, the interpolation?
Sorry?
You mean is there some physics in the corresponding to the interpolation? Or
Yeah, and can we use this interpolation to efficiently, to compute the CFT data in some way, or constrain it? But no, to answer your question, I'm not aware of any physical interpretation.
Any other questions? So I have a question. So this Godin story, does it really apply to any CFT, or do you have some assumptions on the CFT?
Well, it's purely kinematic.
Yeah.
So in this sense, it should apply. I mean, what was important is to have unitary representations. But apart from that, yes, if you have the right representations of SO2 comma D, then it applies to. But yes, I mean, this is partial wave expansion, so it's a kinematical thing.
you mentioned at the beginning, I mean, SO2D, from a point of view of affine Godin models, I guess SO2D is a slightly arbitrary choice. I mean, it sort of seems just slightly random. Is there something much, for kind of, I guess, simpler choices in my mind, at least SUN,
yes.
Do they have physical applications? Or
Right, so the applications there are to some degree applications for SUN, but it has to do with what people do in 4D n equals to 2 supersymmetric theories, and it's quite indirect. So I'm not aware of. The question is, when do these things like correlators and matrix elements, if you want to look for a more direct application, when do these have type A symmetry, right? It just turns out that in conformal field theory, you have a nice SO2, 2, D symmetry. QFT, you would have Poincaré symmetry.
Or even compact Lie algebras in more generally? I mean,
well, for compact Lie algebras, absolutely. You can imagine various systems where you have a family of correlators, matrix elements that have, for example, SON symmetry, right, rotational symmetry. So this would also apply.
Thank you.
Any other questions? Okay, so if not, let's thank Jérémy again. Before you go for lunch, Stein had an announcement.
Right, hello everyone, just very quickly about the conference dinner tonight. So yeah, if you want to go swimming from 4, bring your badge. If you don't want to get lost, and if you want to go alone, that's fine. If you don't want to get lost, Jenny, the conference secretary, will be leaving around here from 3:30. So from in front here, you can just be here at 3:30. You can join a group. It's safer in a group. Then if you just want to show up for dinner or the drinks, that starts at 6. Also, please bring your badge. It'll make it easier for them to check things at the entrance and so on. There will be Ilaria. Is she in the room? I don't know. Okay. Let's see. She was supposed to be here. Okay. She'll be here in 1 second. Okay, good. We'll show her. She will leave here around 5:15. So also, be here and join that group if you want. If you want to go alone, just look at the website. There are instructions on there. Well, oh no, I pressed the wrong button. We have no more website. Okay, it's on the website. I don't know if this is going to restart now. All right, sorry, I'm going to have to log in. This is embarrassing. Good. All right, so yeah, you can see here, for example, you just, you walk a little bit down the street here. That's in that direction, this little blue line. Then there's a tram line that goes along the big road there. You take tram 63. You go all the way to Kölnischer Platz, as it's known, here in Köpenick, and then you take another tram 68 in the direction of Alt-Schmuckwitz, and you get out over here at the Strandbad in Grunau. So that will be right in front of the door. That's fine. The last bit is a nice bit through the forest. If it wasn't 37 degrees today, I would also say you could walk all the way. It's not that far, but I don't recommend it in this weather. Then let's see, any other things I wanted to say. Yeah, so it will be hot today. We decided because of this to move the dinner actually outside, because by 6, 7 the sun won't be so bad anymore, and then we'll have more fresh air. But yeah, everything will be fairly relaxed because of that. So just, dress relaxed, dress for warm weather, and we'll have a nice time tonight. So see you there, and enjoy lunch. Thanks. Oh yeah, sorry, that's Ilaria. Yes. Okay, good. Thanks.